Hello, everyone. Can you hear me?
Yes, we can hear you.
Perfect.
Yes. Yes, Mario, we can hear you. Good morning, everyone. We will wait just a few moments so that everyone who registered for this conference will join us, and then we will proceed.
Okay.
With our agenda. Hi, Olaf. It is nice to see you again.
Likewise.
What time is here what time is in Auckland now?
10 o'clock at night, so nearly bedtime.
Okay. Yeah. I will be very short at the beginning so that you can.
No problem.
Thank you.
Oh, and Damir, you might need to make me a host so I can share my screen as well.
Okay, but I think that you can do it. Can you try it?
Let me try. Yeah, at the moment I can't. Host disabled participant screen sharing.
Okay.
Me neither, Damir.
Oof, I have to check what because now we have a different type of a meeting.
Yeah, I think you go to participants and then right click and make me a host.
Yeah, just a second. Yeah. Okay, I can see it more. Yeah. After I will finish, I have a few slides at the beginning, and then I will make you as a host. Yeah. Okay. Okay. Well, I think that we can start now. It's a few minutes past 10. Good morning to everyone, or good evening to someone, especially to Olaf. It is my pleasure to make you greet you, to express our happy that you are with us in our final conference. So welcome at our final conference of INEX-ADAM project, which was a 42-month project with 5 project partners. So at the beginning, I would like to show you some of main topics from our project, and maybe a few results. And afterwards, we will have really interesting presentations from today's I should say lecturers. And at the end of this conference, I will show you some of the results from our pilot project where we applied our knowledge gathered through this project in specific topics and areas of additive manufacturing application, mainly in transportation, tool making, and medical sector. So I'll start with my my presentation. I hope that this one is okay. I hope that you can see it. Can you confirm it? Yeah, thank you.
Yes.
Thank you. So thank you very much. So as I already mentioned a few times, the main goal of this twinning project was increased our excellence researchers from University of Zagreb in specific topics of additive application of additive manufacturing by aim of our partners. So we are small but very strong consortium, very well positioned not only geographically but also in the field of expertise. So I just spent a few words about the project partners. It's Institute IDEME from Valencia, from Spain. It's LTH Lund University Faculty of Engineering, Montana University Leoben from Austria, and Brunel University from London. And at the beginning of preparation of these projects, we create this type of matrix for definition of our strategic research fields. And as you can see here, all of the partners are present in some of the topics. And in some cases, we have covered from almost 3 or 2 partners some specific topics. So we were really good organized, very well organized consortium regarding the goal of the project. And the main idea is that already researchers from Center for Additive Technologies from our faculty had at the beginning of the project some of the knowledge from additive manufacturing, but the aim was that through a cooperation with training, education with our partners, we will increase our knowledge in some specific fields of additive manufacturing, like material development, material qualification. We learned a lot about functional graded materials. We learned a lot about the design for additive manufacturing, topology optimization, lattice structure, simulation for additive manufacturing, and so on. From the partner from Brunel University, we learned a lot about standardization, and from partners from Spain and Sweden, we learn a lot about medical modeling. And the final goal is to apply our new gathered knowledge from this project to a specific sector like transportation, tool making, and medical sector, as I already mentioned. So everything starts, of course, with standardization. Here we learn a lot about structures of standards, how to apply for a standard in additive manufacturing, because additive manufacturing today is not a tool for prototyping. It's a tool for really serious production of really serious products in serious areas like transportation, like medical sector, where mistakes in production or in previous phases like design, material selection, and so on are not allowed. Then we learn a lot about development and characterization about for metal materials for powder bed fusion from our partner from Spain, from IDEME. From our partner from Leoben, we learn a lot about development of polymer, but also composites of polymer metal and ceramic metal materials for fused filament fabrication. We also learn a lot from our partner from Brunel University from London about functional graded materials and some of application. Here you can see application in transportation industry on the right side of the slide. We also learn a lot from our partner from Sweden about design for additive manufacturing, and also about some of the tools that we can use for this design, like part consolidation, topology optimization, application of lattice structures. And here on the right side of the slide, you can see some of the results of our homework when we were on education in Sweden, in Lund. And few words and few slides only about the possibilities of application of additive manufacturing, which were in focus in our project. The first one is, in this case, medical application, where we can apply additive manufacturing from, for example, production of very accurate models for surgery planning, like you can see here. It's a separation of twins, and the model is presented here on left side, where surgeons can train and educate themselves before the surgery. Also, you can apply this additive manufacturing for production of prosthesis, orthosis also from different type of materials. It depends on application and on certification of the material that can be or cannot be built into the human body. And of course, the next step is production of tissues, and logically, the very last step will be production of the organs. These are the main areas where really additive manufacturing can help a lot. Also, our goal of this project is to research more in deep possibilities of application in tool making sector for both molds for large scale production as well as the molds for a small scale production, because we have a lot of inquiries from the industry for production of few tens or few hundred parts, but with original process like injection molding. So you have to produce a mold. It's not enough to be able to produce a prototype, but you must be also able to produce a final part with the process with which in large scale production the products will be produced. And of course, transportation is very interesting area for application of additive manufacturing. Here you can see example of one Boeing engine with over 300 parts produced with additive manufacturing. On the right side, you can see optimized design of seat support for electrical car. Here you can see one example, or two examples from maritime industry. On the left side, production with FFF technology of the whole boat, and on the right side, impeller produced by additive manufacturing with metals. One of the results from this project with which we are not so satisfied so far is activities of ADAM platform. We were late with this deliverable, but I hope that this platform will serve as a good contact point, not only for project partners, but also for all interested faculties, universities, institutions, companies, and individuals to for future cooperation on further development of application of additive manufacturing in specific topics. I think that here in Croatia, especially education in this area is something that we really must pay great attention. And maybe at the last topic of our conference discussion at the end, maybe we can speak a little bit more about some of the possibilities. I hope that someone from Ministry of Science will join us, but I'm not so sure because I didn't get the confirmation. But from some institutions that are dealing with long life learning, we have some of the representatives here, and maybe we can open a topic at the end of the conference. And I am proud that I can announce that we, as a crown of this project, we finished a book titled A Guide to Additive Manufacturing, which will be published the publisher will be Springer Nature, and I hope within the first half of this year we can expect this book. It will be open access book, so that every one of you will have, if you want, access to this book. And there are some of main topics here in this slide about the areas that we covered in this guide to additive manufacturing. So this is all from my side from the beginning, and now I will ask Olaf. I'm making you a host.
Perfect.
Yeah,
let's see if the technology works, and yes, it looks like it works. So all going well, you'll be able to see.
Yeah, we can see it. Yeah, thank you.
Thank you, Damir. Yeah, good morning. I'm Olaf, and it really is a pleasure to be talking to you guys well, from the other end of the world this morning. And today I'm going to be talking to you guys about additive manufacturing, well, the future of where it's going in the next 5, 10, 20 years, but also some of the work that we've been doing here in New Zealand as part of the ADAM project, together with LTO Lund University in Sweden. But maybe before we start, maybe just one slide of where I am now. I'm at the University of Auckland in a lab, it's called the Creative Design and Additive Manufacturing Lab, which is a really long name, but I describe it as a playground where companies, academic students can come and get their hands dirty and play with the machines, get real firsthand experience. I'm also technically still at Lund University, but of course with COVID, it's been a complete disaster. So I'm supposed to be about a month and a half there each year, but I haven't been able to go for the last 2 years. Hopefully travel will resume to normal and I'll be able to come to Europe again soon, and to Croatia, of course, as well. So I guess what's happening in the near future of additive manufacturing, I guess the first thing is all of industry is wanting to go to bigger volume, so production rather than small volume or prototyping. And that means everything we're seeing, all the work around the world from manufacturers is speed and more speed and more speed, making the machines faster so that you can use them for bigger production runs, make them more cost effective, more economical. And you say, well, why do we care so much about speed? I guess the reason is simple. To my mind, additive manufacturing is probably the most expensive way of manufacturing anything in the known universe. And the reason it's so expensive is because it's so slow. If it takes 1 second to injection mold a part, but it takes 20 hours to additively manufacture the part, then you can start to see why the speed of the system becomes a bit of an issue. And I'm going to talk a bit about some of the ways that manufacturers are working on speeding things up. But right now, today, with the slow systems we have, design for additive manufacturing is still one of the main tools we have. So several ways of speeding machines up. The one we're seeing most of is, at the moment, more lasers. So this, I'm talking powder bed fusion, but the same thing applies to resin vat photopolymerization. So SLM Solutions do a machine called the Cube, which has now got 12 lasers in it. Right now, the most lasers typically is 4 lasers. EOS with a laser profusion, they're working on a system with 1 million lasers. So it's 1 million laser diodes, and as the print head goes across the bed, the powder bed, the laser diodes switch on and off. We all know about companies like HP with a multi-jet fusion or high-speed sintering, where they try to melt the entire layer at once rather than the scanning process of the lasers. And we'll talk about that a bit more in a few minutes. But as I said, today, these techniques, even with 12 lasers, it's still not a fast machine. So to my mind, design for additive manufacturing is one of the main ways we can speed up the process, which helps a lot. So my first tip is excess material is your worst enemy when it comes to additive manufacturing. So any material that's not serving a real engineering function, adding value, get rid of it. Because that material takes longer to melt. The laser has to melt, fuse that material, and you're going to increase residual stress, which means you've got to heat treat the part for longer. The part's going to weigh more. The material cost is going to be higher. So get rid of material. And many of you will have seen this slide before, because we've all talked, and Damir mentioned it earlier, topology optimization as one of the tools for getting rid of material. So topology optimization, effectively, it's using mathematics or finite element analysis to analyze your part, and anywhere that's not under stress, get rid of material in that area to lighten the part. So this is a titanium bottle opener that's on my keyring. If you look at the one on the left, if you're going to make it the traditional way, you'd start with a block of aluminium, would weigh around 10 grams. You'd put it on your CNC machine, you'd machine away the center, and the center bottom is what you'd have as your finished product. And you will have all seen similar bottle openers to that at the gadget shop. In contrast, the topology optimized one is less than a gram. Think about that. That's a 90% weight saving of that over that original block of material. So that weight saving is not just a 90% weight saving, it's a 90% time saving, therefore a 90% cost saving as well. So maybe another real world example of that, this is some of our students at the University of Auckland did this at a startup company. So they're now selling these 3D printed mountain bike brake calipers, also topology optimized. And in this case, 45% weight saving over the conventional machined brake calipers that they normally use. Now, for a performance biker, that 45%, that's the difference between winning and losing a race. So, money is no object for that. Maybe a Swedish example. It was started with a student at Lund University called Henrik Nilsson. So it was a hydraulic manifold for Atlas Copco. So what you see on screen there is an underground drilling rig. It's a great big tractor that goes into mines and drills holes. Where that arrow is pointing on the right-hand side, it's an engineering product called a hydraulic manifold. So a manifold is a block of steel. I'll show it to you on the next picture. It's a block of steel with a whole bunch of holes drilled into it, and you block some of those holes. And the idea is you form a network of pipes so that you can get hydraulic fluid from one place to lots of other places. So this was the original hydraulic manifold that Atlas Copco was using, and they were interested in using additive manufacturing to see if they could make it better, lighter, and so on. So we redesigned it from what you see on the left to what you see on the right there. So it's gone from 16 kilos down to 1.4 kilos. So that's a 92 or 93% weight saving. I mean, that is huge. So the weight saving on this meant they were able to lose one of the big concrete counterweights they put on the back of the tractor because of the weight saving on the front. So let me just give you a couple of more slides before we get the fun future stuff on why that excess material is such a big challenge for additive manufacturing. Really, really simple example. It's another manifold, because manifolds make good examples for weight savings. So what you see there is a hydraulic manifold, 100 millimeters by 100 millimeters by 100 millimeters. So 100 millimeters cubed. And you imagine you take a slice through it, which is one slice of the additive manufacturing process. And you imagine it's effectively like on a piece of paper drawing a square. And if you want to draw a black square, you draw the outside of the square, and then you drag your pencil backwards and forwards to color the inside black. Most additive manufacturing processes, whether it's FDM, material extrusion, or resin, or metal, or polymer powder bed fusion, it's the same process, but it's a laser drawing backwards and forwards. So 100 mil by 100 mil is your square. Now imagine your laser is traveling at 0.1 mil spacing. So it's going backwards and forwards to make the square black. So think about how far the laser has to travel to melt one of those squares. Now I won't ask you for the answer, I'll give you the solution there. So you can see on the right, that's your slice. The blue lines are the lines the laser has to travel. So if it's 0.1 mil hatch spacing, which is pretty standard, that means for that tiny square, that 10 centimeter square, the laser has to travel over 100 meters to melt all that material. Now think about that, that's 100 meters of laser travel. So if the laser is going at, let's say 330 millimeters per second, which is about right for a 100-watt laser, that's 5 minutes per layer, or $5 per layer if you work out $65 an hour for machine time on that. So you think, oh, that's not too bad, 5 minutes, $5, that's a bargain. Now remember, our cube is 100 mil tall. Let's say the layers are 50 microns thick, which is actually quite thick for a metal printer. That means you've got 2,000 layers. So think about that. You can now got $5 times 2,000. Now you start to understand why that excess material is your worst enemy. So next example is the same manifold. This is not designed for AM. This is just to show you the effect of reducing material. Imagine we take that manifold and we shell it. So we give it an even wall thickness all around. All the pipes have a 2 millimeter wall thickness. The outer walls have 2 millimeter wall thickness. So this is what it looks like. And on the right, you can see a slice of it. So now the laser only has to melt that outside border and the cylinders that make up the cubes. So that the distance the laser has to travel has gone from 100 meters for the solid cube down to 4.5 meters for the shelled cube. As I said, this is not really a good example for design for AM. I'll show you a better example in a few minutes. But we've gone from 5 minutes to 13 seconds, or $5 to 24 cents per layer. So you start to see why getting rid of excess material becomes really, really critical. A couple more slides before the fun stuff. Support material. So for those of you who have printed in metal or in material extrusion, so FDM, or even in resin with SLA, you will know about the evils of support material. It's material, sacrificial material that you have to remove after printing and throw away, dispose of, recycle. So 2 tips I can give you to minimize support material. If you think of support material as a temporary wall, well, why not think of it as a permanent wall that becomes a feature of your part? So replace the temporary support material with a permanent thin wall that acts as a support and becomes a feature of the part. And I'll give you the example in a few minutes. And the other one, of course, is changing the angle. So typically anything below 45 degrees, you're going to need support. Anything above 45, you don't need support. So think about your angles. Just to give you some numbers on that, if you, this is a survey of service providers that provide additive manufacturing as service. In metal producers, about 45% of the cost of the part is not the printing of the part. It's the work you do before and after. You know, that's huge. So over 30% is the work you do after you print the part, removing the support material. So to illustrate that, I'll show you one of, for those of you who don't know me, one of my hobbies is making electric guitars. So I 3D print electric guitars. And this is one I did a few years ago, and it's printed in aluminum. And what you see there on screen is the guitar body still welded to the build plate. So that aluminum plate that it's sitting on, the whole guitar is welded to that. This guitar, it's sort of barbed wire themed with flowers inside. And I'll give you a close-up of that. So you can see the barbed wire on the top and on the bottom, and in between, support material. If you look at the flower on the left-hand side, you can even see support material underneath the petals. So all of that support material has to be removed by hand. And that is an absolute nightmare. I mean, that is hard work. So the finished product, if I may say so myself, is, you know, quite a nice looking guitar. The print time was not too bad. It was 9 hours. It was done on a big EOS M400, a 4-laser machine. So 9 hours to print was pretty reasonable. The first one I built took me 4 days to remove the support material. So my hands were bleeding by the end of it. It was hard work. And then another 4 days of sanding, filing, shot peening to make it look really nice. The second one I built 2 of these, took me 2 days and 2 days. It was much shorter because I knew what I was doing and I knew the best technique for it by then. So as I said, thinking about support material and thinking about minimizing mass of material, so unnecessary material is critical. So let's come back to our manifold. So if we look at our previous block manifold, I'm now doing more of a proper design for AM process to it. So on the very top left is my starting point. The top middle is the shelled manifold. So what I've done is I've shelled it out, and that is the bare minimum functional manifold. It's the pipes that lead the fluid from one place to lots of other places. On the top right, you see that minimal design on the center with support material. So that blue material is sacrificial support material that afterwards I'm going to have to spend my labor, my very expensive labor, to break off, remove, throw away, or recycle. So what I've done on the bottom left is I've taken those blue temporary walls and I've replaced them with solid permanent walls. They're thin walls, they don't add a lot of weight. They only add a tiny amount of weight. And you'll notice I've put elliptical holes through them to minimize that weight as much as possible. And in the center bottom, you can now see how it's printed with support material. So only a tiny bit of support material to weld the part to the platform, and that's it. So which means after you cut it off the build platform, your part is ready to use, no other post-processing necessary. And you see it on the right, they're printed in Inconel, which is typically a fairly hard material to print. So it shows the technique works. And again, huge cost reduction. So just to give you the cost before we get on to the fun stuff is, you know, the solid block. And these are quotes from an online bureau. I think it was Sculptio or iMaterialize. I can't remember which one. $15,000 to print that block of steel. I mean, it's crazy. Nobody in their right mind. So 191 hours to print. In contrast, the design for AM1 on the right, 19 hours to print. The middle one, the shelled one, goes from 15,000 to 4,000, still expensive, down to under 2,000 for the design for AM1. Is it worth 2,000? That depends on the context you're dealing with. But I can tell you that Atlas Copco one I showed you earlier, when we did it for real in Sweden, the printed one cost about 20% more than the CNC machined one. I redesigned it here in New Zealand last year, and we printed one here. And because machines have gotten cheaper and faster over the last few years, it costs the same to print as it costs to machine. So to finish off the design for AM side of things, the ultimate goal of design for AM is minimum material and minimum support. And to give you one example of that, anybody gets into metal printing, I can guarantee that sooner or later you're going to print a bottle opener. So these are University of Auckland bottle openers, very, very light. It's a one-handled bottle opener. So you can see my hand on the left side. And if you see where my hand makes contact with the bottle opener, it's not solid. It's a thin structure with a scaffold in between to make it lightweight as possible. And on the right, you can see a sea of them, a little army of them printed. Again, no support, just a single little pin joining them to the platform. You break it off and they're good to go. Not only that, but the post-processing, the automated polishing we use. So to go from the raw state that you see on the top left there to the polished state on the bottom left, no human labor. So we use centrifugal, high-speed centrifugal polishing for that, where you throw them into barrel, the barrel spins one way, the big drum spins the other way, and it automatically polishes them to that level, which is a very, very useful thing to do because labor is expensive and painful. So as I said, that's my first messages is, if you want to speed up your processes, get rid of masses of material. Now to look at some of the other future trends where we're heading in the near future, larger sizes. So more and more companies are working on large scale additive manufacturing systems. This is one from Aeroswift. It's Aerosuit is a company in South Africa where they're developing a large titanium printer for the aeronautics industry. The print size is 2 meters by 0.6 by 0.6 meters. So a fairly high volume, powder bed fusion system for metal. China is working on similar large scale system. Around the world, there's now material extrusion, sort of a large, big area additive manufacturing systems that'll do, entire ship hulls. I think Damir showed us one of those earlier, where they're doing entire ships in one go. Another example of large scale, this is Airbus working on printing an entire airplane fuselage. Now, this one, of course, is a prototype. I wouldn't want to go flying in that. I wouldn't feel too safe trying to fly in that, but it gives you an example that everybody is trying to go bigger and bigger and bigger. And I suppose one other future area, although it's happening all around the world now, and I'm not going to spend a lot of time on it, but house printing. We're seeing all around the world people printing houses in concrete. So again, large scale 3D printing, extruding concrete layer by layer by layer. I think this is one that was done in Germany last year. So around the world, people are working on trying to print a house in 24 or 48 hours using automated printing systems, and they are working on automatic electrical systems and plumbing systems that you can plug and play as you print around that. Another interesting area of research, and we've been doing some of that in New Zealand, and it wasn't really part of the ADAM project, but we did some of that, quite a bit of that at Lund University, printing food. It's an interesting area. Now, food printing has been around for a long time, but mostly, I'd say 99% of it around the world has been food extrusion, where you put your food paste into a bag or a syringe and you squeeze it out and then you reshape it into a new shape. So it's not really printing food, it's reshaping food, but really, really big interest in food for the elderly. So you can print food for elderly people who can't chew and swallow, for example. The problem with material extrusion, by far the biggest problem, is it's very, very hard to scale. So if, for example, one steak takes 10 minutes to print, that means 100 steaks is going to take 100 times 10 minutes, which means it becomes hard to scale for big production industrial quantities. So some of the work we've been doing, which is a little bit different, is instead of using material extrusion, is we're using binder jetting. So binder jetting works with powder-based material. So you have a powder-based protein and you spread a layer of it, and then you inkjet print binders and additives onto it. So you inkjet print glue onto it to bind it together. And because you can have multiple print heads, you can be printing on other additives like vitamin C or calcium or flavoring or color and so on. So the idea with this is being able to scale it up to do production quantities of food. And again, every bit of food you print is customized for each particular patient, for their particular nutritional needs. You can do it to their flavor and so on. So this is new work for us, the whole binder jetting area of food, but we've been successful. So we've printed chocolate, sugar, those were fairly easy. We've now printed rice and chickpea, sort of meat alternative protein blends of powder that we can successfully print now. We've in the lab, we've got a big bag of meat waste powder that we're trying to print with. Problem is it doesn't smell very nice. So we're trying to figure out the technical parts of being able to print it in a way that makes it attractive. So as I said, that's just another area of future additive manufacturing. And I think the next one I just want to mention briefly is the new breed of software, I guess, computational design or design automation software we started to see appear on the market over the last, particularly the last 2 years or so. So this is software like, for example, Gen3D or Topology, just to name a few of them. So what makes this software different to your standard SolidWorks or Creo or CATIA, your CAD package, is it represents geometries by using equations rather than B-rep surfaces or what have you. So that makes it incredibly efficient for computational design and design automation. And we've been doing a lot of work with it over the last years to try to automate design. And one example, and I think Damir showed a similar slide earlier, the idea of making prosthetic sockets for amputees. So this is done, we did in Topology. This is the workflow. And on the left there, you can see 10 different sockets. Each one of those custom prosthetic sockets for a real amputee. So this is a scan of the check socket. You import it into Topology, and in about 2 or 3 minutes, it designs a ready-to-print socket that's perfect, that'll fit the customer perfectly. All you do is you set the thickness you want, you can set patterns on them and so on. So that ability to very, very quickly automate a design flow is hugely powerful. And another example of that, so what you see on the top left there, that's my hand scanned, it's a scan of my arm. And in the software, you set the trim line. So you say, I want a trim line here, here, and here. And in about 30 seconds, it'll generate you a perfectly fitting splint or cast that you can print, and it'll fit you perfectly. And you can choose the pattern, whether it's a Voronoi or a smiley face or a Hello Kitty on it, whatever you want to make it attractive. And what's really cool about this is we print them in nylon and SLS, which means they're dishwasher safe. You can throw them in the dishwasher when they get dirty. You can wear them in the shower. And the big thing, of course, particularly if you look at the white one that I'm wearing, is you can breathe, so you don't sweat as much, so they don't get as smelly. And the really good thing is you can scratch yourself when it gets itchy, whereas with a standard plaster cast, that's much harder to do. And one more of this design automation software that we did just this year. This was a Kayak Arm. So this is a professional amputee kayak racer. So Sharon Dag is her name. She races in kayaks, and she needed a special kayak arm that fit her perfectly and allowed her to grip the paddle. So we did a ball joint for the paddle that allows some movement on the paddle. And again, that design automation, literally in a few minutes, you can now change it for a different amputee that might have a missing leg or a missing wrist, and very, very quickly change that automation. And I thought I'd give you one more example of design automation that we've been working on a lot over the last year, is the ability to do these funky gyroid structures. So TPMS, triply minimal periodic surfaces. So what you see on the left there is a single gyroid cell. Gyroids have been around for many, many years as a mathematical dream. You could design them, but you couldn't do anything useful with them. But with additive manufacturing, you've suddenly got some amazing structures that you can now very easily print. And what makes them particularly attractive for additive manufacturing is these structures are generally self-supporting. So you can print them at quite a large scale with no support material. And that makes them very, very attractive. The other thing that makes them very attractive is they have a huge surface area. So if you're thinking about heat transfer application like heat exchangers, they are incredibly powerful tools. So what you see on the left is a single cell. On the right, you see a 2 by 2 by 2 cell. And the red is the hot side, the blue is the cold side. So we've been doing a lot of work on doing heat exchangers using this technology. So what you see there on the left is an air to liquid heat exchanger, so a radiator in other words. And on the right, you see a liquid to liquid heat exchanger. So with the liquid to liquid one, the hot goes in the left side, comes out the bottom right, and the cold goes in the opposite way. And you get a crisscrossing diagonal, and you can see on the top right there, the maze of hot and cold water that are intertwined. So that the heat from the hot water is getting removed by the cold water and coming out. We haven't yet done the proper scientific tests with temperature drops and pressure drops and so on. So it's been very unscientific, but we poured boiling water in the top, and I can put my hand on the bottom or the other side, and it comes out at shower temperature. So that's how efficient these technologies are. And again, what's cool about the workflow we've done is you can design your overall shape in CAD, in SolidWorks or Creo. You import that into Topology, tell it the wall thickness, the cell size, and so on, and it automatically generates a ready-to-print heat exchanger in a few minutes. And as I said, that is where the power is that design automation and to be able to reuse your workflows again and again and again. Damir talked a little bit earlier about injection molding tools and conformal cooling channels. So that's another area we've been doing a lot of work in, but maybe in a different area to what you guys have been working on. So conformal cooling channels are well known. It means instead of straight drilled holes, you can have nice curvy channels following the curve of your part. That's well known. The area we've been working on quite a bit is, again, when I talked earlier about minimizing the mass of material you have to print. If you think about most injection molding tools, anywhere between 1/3 and 2/3 of the injection molding insert is actually quite a boring lump of material. It's only about 1/3 to 1/2 that's interesting with all the conformal cooling channel. So we've been working on a hybrid approach where the bottom boring part of the tool, we CNC machine, we mount that into our 3D printer, our metal machine, and then we print the interesting part with the conformal cooling channels on top of the machine part. So it's a hybrid approach where half of the tool is machined, because that's much more cost effective for the plain part with just pipes drilled into it. But then the interesting part with the conformal cooling channel we print. We've done these in aluminium with 3 different grades of tooling aluminium, and with tool steel with 3 different grades of substrate underneath. And of course, a lot of the work we had to do was to make sure that the interface, where you've got the machine part and the printed part, that interface is good and is not going to break. And the good news is that in all our tests, it never fails at the interface. It always fails on the weaker of the 2 materials. So if the substrate material, the CNC machine material is the weaker, that's where it'll break. And that's what you see on the 5083 and the 6081 aluminium. But on the Alumec, which is a tooling grade aluminium, it breaks on the printed part because that is the weaker one. And we found exactly the same thing with steel tools, with maraging steel and I think P20, 17.4 pH, a bunch of different substrates. So just to show you a real case study we did for a manufacturer called Camex. And what you're seeing there is an 8-cavity tool for bottle caps done with all the inserts are additively manufacturing using that hybrid approach where half of it is machined, half of it is printed. And the big difference here is the cooling time went from 4.5 to 1.7 seconds. I mean, that is a huge difference. That speed advantage, so the cost to print the 8 cavities, the 8 inserts, was about 20% more than the conventionally machined old tool that it replaced, but it paid for itself in less than 2 weeks of running the tool. So because of that increased cycle time, within 2 weeks, it had paid for itself. So that became a no-brainer for the company. They're now very heavily invested in this whole idea of hybrid additive manufacturing tooling. For those of you who are interested, to shoot me an email. We've got another paper we're about to publish on this area, so I'll be happy to send it to anybody who's interested. Other future areas we're starting to see is, we're starting to see, but we still have a long way to go, is materials designed specifically for additive manufacturing. By far and away, 99% of the materials we use today for additive manufacturing are conventional injection molding materials or conventional casting alloys, and we use them for additive manufacturing, and they work, but they're not optimized for the process. So Scalmalloy is it's done by AP Works, which is I think it's a German company. It's now owned by either Airbus or Boeing. I forgot which one. So it's an aluminium alloy with a bit of scandium added to it that is specifically designed for additive manufacturing, and that makes a huge difference. So we need more of those materials. Damir talked about this earlier, sort of functionally graded materials. So there's a huge amount of effort around the world now to improve functionally graded materials. And 2 ways people are looking at it. One is to change the material itself. So for example, that example in the middle, going from titanium to Invar, where you start with pure titanium, then over the course of maybe a centimeter, you gradually alloy in more and more Invar, and then you end up with pure Invar. On the left there, you see HP, where HP's multi-jet fusion process, because they're ink jetting on agents onto the ink, they can now print, for example, invisible QR codes, or make some parts of it flexible, other parts of it rigid, by changing the agents they're printing on their nylon powder. So as I said, changing the material itself is one way. The other way, which you can see on the center bottom there, is changing the geometry. So instead of changing the material, you change the geometry to be solid in some areas, have a certain lattice structure in another, a different lattice structure in a different area, so you can affect the flexibility of it in new ways. So there's one other interesting new material I want to talk about, but before I do that, I'm going to show you some of my latest 3D printed guitars, because the new material I want to print about, I also happen to have tested in a guitar. So as I said earlier, when I showed you that aluminum guitar, one of my hobbies is making guitars, and they're all 3D printed. I'm actually a bass player rather than a guitar player, and I'm a huge Beatles fan. So about a year and a half now ago, I printed myself out a Beatles themed bass guitar. For those of you who know the Beatles, you'll see it's shaped after Paul McCartney's violin-shaped bass. It's a Höfner bass shaped like a violin. The music on the front is the score for Yesterday. And inside the guitar, you've got iconic scenes from the Beatles. I think I've got a close-up of it on the next slide. Yeah, close-up, but you got the Abbey Road scene where they're walking across Abbey Road, Yellow Submarine, George Harrison's guitar, John Lennon's glasses. In the bottom right, it's a bit hard to see there. That's the drum kit from the Sgt. Pepper's Lonely Hearts Club Band album. It's a very famous drum kit. And this bass guitar is printed in nylon, so it's printed using SLS, so in white nylon. And all of the inside of it is hand painted by hand afterwards. So my wife is an artist, and she very kindly painted the inside of that. And I swear by the end of it, I think she hated me, because it was really, really hard work to paint. I mean, that drum kit is actually painted with yellow and red and gold lettering on the front. I really need to get a better picture of it to show you the close-up. But because of this really, really hard job of painting it, I decided to investigate color 3D printing to see if printing in full color. It's been around for many years with Z Corp machine, and then Stratasys came out with their material jetting systems, their object systems, and then the Connex. So I wanted to see how good it was. So this guitar is one I did just over a year ago, and this is printed as you see it there in full color. So no painting at all. It's printed straight off the machine looking like that. So well, it comes off the machine with a wax support material. So it's a soluble wax. You throw it in an ultrasonic tank that dissolves all the wax, and then you're left with that. So the only finishing I've done to that is I've given it a clear coat with a matte clear. So as I said, this was done purely for fun to see how good color 3D printing had become. And I was so impressed with it that we actually bought one of these machines. So we've got one of these machines in our lab, and I'll show you some of the other work we've been doing that. So again, I mean, Damir mentioned medical models, for example. I'll show you some of the work we've been doing in that particular area. But as I promised a few minutes ago, I'm going to show you a new technology, new material that is of interest. So it's the latest guitar I did just, I think, about 2 or 3 months ago. So this guitar is printed in wood. So the material in here is actually sawdust. It uses binder jetting. It spreads a layer of wood sawdust, so wood waste material, and it then inkjet prints bio-epoxy, so epoxy made from lignin, also waste wood product on top of it to bind it together. So that is a really, really interesting new material, sustainable material, because it's made from waste product. And you see it there as a different colored epoxy to get the wood grain color onto it. And again, this particular design, I did it also in topology. So that lattice, that spiral pattern you see there is a diamond cylindrical lattice. So again, now that I've got that in topology workflow, I can change the design instantly, develop 100 new designs with different gyroids pretty much instantly to get it ready to go. But as I said earlier, so as I said, new materials we need more of, unquestionably. And this was just an interesting one. And I decided just to try it because it existed to see how good it was. And I was fairly impressed with it. The bad news or the good news is I've now got to build another 4 guitars like this, because now the manufacturer of the machines wants 2 guitars to show around at trade shows. And then I've sold another 2. So coming back to the color printing, I mean, that has really changed. I mean, this is a future area of additive manufacturing growth. Medical models is huge. So an aorta on the left-hand side there, where it's an aorta with a stent in it. So if the doctor's got to do a stent operation on you, they try to explain it with words or videos. You can't understand what they're talking about. You show the patient the model, and suddenly they can understand what it is you're talking about. On the right there, you see eyeballs. We've been doing a lot of work with eyeballs, and just in the last 2 months, there's been several people using these as prosthetic eyeballs, as eye replacements. Now, the reason we did it wasn't for prosthetics, and now we're moving into that area. And we did it to see if we could fool facial recognition on an iPhone. So I'll talk more about that in a few minutes. I've only got a few more slides to go before I finish off and we open up for questions, but I'll talk more about this. But just to show you one more biomedical example, being able to print, for example, these human bodies. So we printed out a whole bunch of these anatomically correct Barbie dolls. So again, in our model, and then you can get these models from MRI data from fairly easy. You can hide and show the organs you want and print educational models where you show just the skeleton embedded in clear resin. So that's the beautiful thing with these printers is you can print clear and full color. And on some of them, you can also print flexible material. What you cannot do yet, unfortunately, is print clear, flexible material. That's coming soon, because the dream of the doctors is to be able to physically practice their surgery on a printed version of you before they do it on you for real. And of course, now with hard materials, you can't do that. You can visualize, you can plan, but you can't physically cut the material to practice your operation. Well, you can, but the material, the rubber material is a black or a gray material, which means you can't really see what you're doing. So we need clear, soft material. But that is coming soon. So my last example before I finish off is really just something we've been doing for fun. So as I said earlier, when we got this color printer, we decided to see if we could fool the facial recognition system on mobile phones. So the first thing we did is we scanned my face, printed it out pretty much in one piece, and we were amazed by how good, how realistic it looked. And that was good enough to open a Samsung or OnePlus facial recognition. But it wasn't good enough to fool the iPhone. So we think the reason why is the iPhone expects movement. It expects you to be able to move your eyes. So this is the second iteration where we printed my face. And in this one, we've separated out the eyes. And you can see the eyes are movable eyes, just to see if it could fool the iPhone. So as I said, this particular one, unfortunately, still doesn't fool the iPhone. The reason for that is these eyes are not my eyes. I just made an iris in Photoshop and put it on, and it looks sort of like my eyes, but it's not actually my particular iris pattern. So the next step we need to try is to try to do a photo of my eyes and then put that onto the eyeball to see if that'll then fool the iPhone. I'm quietly confident we will be able to fool it, but we'll have to wait and see. Watch this space, and as soon as we get results of that, I'll tell you more about it. So yeah, just aware of time. I think I had about 40 minutes to talk, or 35 minutes to talk, and some time for questions, I think. So I'll finish off there, and happy to answer any questions about, well, any of the work we've been doing or any of the work we're planning to do in the near future, or absolutely anything else you want to ask me about. So thank you very much for listening.
Thank you, Olaf. It's a really interesting presentation, and I should say that it's a pleasure always to be present at your lectures like today. So thank you very much for your look ahead in additive manufacturing application, new developments, today's advanced application of these technologies. So far we have one question from Hrvoje Hršak in chat. He asked, okay, first of all, he said, great presentation, but what are the strategies if you need more structural strength on your printed product? How to calculate how much supporting material should be removed in that case? So
yeah, I mean, so that's actually a really, really good question. So the proper way of doing that is to simulate your print before you print it, to run a simulation on it. And Magix, Autodesk, NetFab, so most of the pre-processing software for it now have simulation capabilities built in, where you can simulate your print, including the support material, and it'll tell you if a part is going to have enough stress to detach from the support and cause the part to crash. And in fact, you can even compensate your parts. If you know your part is going to bend up because of the stress, you can change the model to be downward so that it ends up being in the straight position after you print. So if you're new to it, I highly recommend running simulations first. I now don't run simulations anymore. I find simulations sometimes take a whole night to run, and I'm just not that patient. So I now have enough experience for it to be able to look at the part, understand where the stress is. Again, coming back to what I said earlier about removing unnecessary material, if your part is well designed, there's actually relatively, you can design it to have relatively little residual stress in the part, which means the forces on the support will not be as great. In terms of strength of your general parts, if you remove material, finite element analysis. Always do an analysis of your part to make sure that it will withstand. So if you topology optimize a part, it's vital, it's critical that you run a good finite element analysis on it to make sure it's going to be able to withstand the forces that you're going to be acting under. So yeah, absolutely. Oh, somebody was asking about the eyeballs and one of the dolls. Okay, so Per Gustav was asking about the Barbie dolls, the anatomically correct Barbie dolls. So I've printed them. Normally we print them at about 30 centimeters high, but I've got one in my living room that's 60 centimeters high. So, you know, a reasonably big one. The cost to print them varies. So the eyeballs, they're full human size eyeballs. They cost between 10 and 15 New Zealand dollars. So call it 10 euro to print. The cost for the resin for these color printers works out to about 250 New Zealand dollars, so probably about 180 euro a liter for the resin. Horrifically expensive, I think, but then if you compare, so the printer we've got, the brand we've got is a Japanese one by a company called Mimaki. The competition is Stratasys. Their resin costs between anywhere from 600 euro to 2,000 euro a liter. It gets really, really, really expensive to run. That was the reason we bought the Japanese one. The quality, the print quality is similar, but the running costs were quite a bit different. So that's why we went with the Japanese one.
Thank you, Olaf, for answering. Do we have maybe one question more? So the last slides you have showed us really remind me on the Mission Impossible serial of movies. Okay, thank you.
It's a little bit frightening. It's yeah. So frightening, and the hairs look like, if you haven't shaved and you scan and you print, it looks like you haven't shaved. I mean, you can see every hair on it. It's pretty amazing.
I see the possible application in humanoid robots of this application.
Absolutely. Yeah. I think Anna has a question, I think.
Yeah. Anna.
Hello, Mr. Olaf. Do you hear me? Anna is here.
Perfectly.
Okay, so you said that you bought this Mimaki machine and that the problem is that they do not have transparent. And what about rubber-like material?
Yeah, so they have transparent material. They don't have rubber material.
Rubber.
Yeah, the Stratasys machine has rubber materials, but only in black, and you can mix in some white to make it gray. So we need transparent rubber. So we've got hard transparent, but not soft transparent. So what we need is like a soft silicon translucent material for medical models that you can physically cut to practice your surgery. So if you, Anna, if you or anybody else can come up with that magic material, that will be a game changer.
Yes, because I went in Formnext to their booth, and they also impressed me, and I think that they have some distributor in Croatia also, this Mimaki. Yes. So, but I know that Stratasys is bigger let's say firm, and they have really lots of material, but they are expensive, really expensive.
Yeah, I mean, the big challenge, one of the other universities in New Zealand has a Stratasys machine, and the students can't afford to print on it. So we print the university students because ours is a bit more affordable. So it's a challenge.
Thank you, Mr. Olaf.
Thank you.
Thank you once again. Olaf, thank you for really nice presentation. I hope that you impressed all of us. I'm sure, and that you open some new ideas for a lot of us who are dealing with additive manufacturing. And thank you for participating from the different part of the world in different time zone. And thank you for supporting our project from the beginning until the very end. Thank you once again.
Absolute pleasure.
I would like to ask you just to return the host so that I can.
I don't think I need to. I can try.
Okay. Now, okay, I'm now the host, okay? And I will ask Mario from IDEME.
Yes, hello.
Yeah,
Damir.
you're with us. Oh, hello, Mario.
Hi.
Mario will show us some overview of the projects from IDEME Institute in also area of additive manufacturing, and maybe open some new perspectives of possible application of the additive manufacturing. So Mario, please, the floor is yours.
Okay, can you see my screen, guys?
Yes, yes.
Okay, first of all, Olaf, thank you for your presentation. I guess that we are aligned in the same topics because we have been working on additive manufacturing for plenty of years. So I guess that most part of the things that you mentioned will be included in my presentation. So good morning, everyone. Hope you are enjoying this conference. My name is Mario Martinez Ceniceros from IDEME. And first of all, thank you, Damir, and the whole INEX-ADAM team for organizing this forum today. I'm very glad to represent IDEME in this speech. So from now on, you will be able to see my contact details for further discussions in the bottom part of the slides. So without any further ado, I will start presenting our activities. Okay, so as a very quick introduction, IDEME is a technology center based in Valencia on the east coast of Spain. We are the result of a merging between IME, which was mainly related to metal processing, and IDEMA, which dealt with furniture and packaging. So this merging took place in 2016, and since then we both work towards the same goal, which is helping and supporting the industry. We currently have two headquarters located in Paterna in Valencia, and actually they are very close to each other, like 5 minutes on walk. So as I was saying, our main challenge is to support the industry, to increase the competitiveness of companies in the field of design and development of innovative products, materials, and processes, logistics, distribution, and services by and large. So our main activities are research and development projects, as it is the case of INEX-ADAM. So we are currently working on several proposals, not only at national, but also at the European level. We offer advanced technological services to the industry so that they can integrate those solutions to their value chain. We offer also a wide range of laboratory tests and analysis, you will see later on, and technical training of companies as well. And last but not least, we act as a technology observatory. So basically, we analyze the market and work on business strategies. I would like to briefly mention the different units that IDEME is made of, because although I'm here representing the additive manufacturing department, IDEME has a wide expertise in some other matters. So as you can see in these slides, we have 9 complementary lines of activity where companies can find support in. So as you can see, the first one is water and liquid waste treatment. This unit is mainly related to the elimination of pollutants and recovery of substances in water and liquid waste. Additive manufacturing, I will go over this in the next few minutes, so I will not spend so much time. Product development, so as the name says, development of new products and systems, design, calculations, simulations, Internet of Things, and etc. Industry 4.0, which is integration of information and communication technologies in the supply chain, advanced applications of materials, modified surfaces, toxicity of materials, and intelligent packaging and biomaterials. So as you can see, these 9 lines of activity are very complementary, and in some occasions we have common projects. I will now focus on the unit I belong to, which is additive manufacturing technology. So we started working on 3D printing in 1997. So therefore we have more than 20 years of expertise on this matter. Within these years, we have had the opportunity to understand how these processes have evolved, and we are now able to identify where is the additive manufacturing likely to move in the next few years, and the future trends as well. So in these slides, you can see all the technologies that we do have at home at this moment. So the great thing about our facilities is that we cover almost all the 3D printing techniques available in the market, as you can see. When it comes to powder bed-based technologies, we have two electron beam melting systems, the RCAM-A2, this one, and the RCAM-A2X, which actually is from GH Induction, a company we made a development for, but this machine is operated at IDEME. I will talk a bit about this development later on. So these machines are able to process metal powders as titanium alloys, pure copper, nickel-based alloys, between others. On the other hand, we have, we have 3 laser powder bed machines that can produce metal parts as well. One of them is fully dedicated to a project named Custodian, this one, the gray one. I will briefly explain later on. And 2 dual laser machines from Prima Additive, these blue and orange machines. So these equipments can produce metal parts from aluminum alloys, stainless steel, titanium, copper alloys, cobalt chromium, and so on. So different materials, let's say. Regarding powder bed fusion technologies of polymers, we started working on SLS, selective laser sintering, some years ago. And it was in 2019 when the multi-jet fusion from HP was added to our portfolio. We also have resin-based machines as stereolithography, digital light processing, and liquid crystal display. I have to say that we attend all the Formnext conventions during these last few years. And these processes are now in a growth stage that we believe that we will see very interesting equipments in a few years, thanks to the part accuracy that they can reach and the production ratios to be offered. So as Olaf said, additive manufacturing is moving towards more productivity, and we can clearly see that these kind of technologies are offering these high production ratios. So this new year, 2022, we have 2 new equipments that are going to be installed at IDEME. On the one hand, a very interesting hybrid system which combines laser metal deposition and computer numerical control. With this equipment, somehow we will be able to cover certain areas that cannot be addressed with powder bed fusion. It basically adds metal layer by layer by means of a LMD head that afterwards is machined to reach the final part. So basically with the LMD, we get a near net shape part that is finalized in the post processes in the same machine. The build area of this process is way larger than PBF, and therefore bigger applications could be addressed from now on. On the other hand, we are working on the processing of concrete via additive manufacturing for construction and architectural purposes. So as Olaf shown in his presentation, some houses are being actually built by additive manufacturing. So I will explain a little bit about this project later on. And last but not least, we also have material extrusion, that one, systems to completely cover our portfolio. So some fused filament fabrication desktop machines that are mainly used for training, and the Mark IV II, which combines a matrix made up of polyamide with continuous fiber. So this is a very interesting technology for tools, clampings, high strength demanding parts, and so on. So all in all, we have a nice overview of the additive manufacturing scenario at our facilities, which makes IDEME interesting as a partner in additive manufacturing. So as you can see, every year we try to be up to date, complementing our portfolio with the latest technologies that emerge into the market. And as I said, additive manufacturing tends to be faster and faster every year. So some years ago, we worked with SLS machine producing parts, but this productivity has been overcome by the multi-jet fusion, which also works with polyamide, but the processing time is quite faster. So as we have seen our facilities already, I will now focus on the main activities of my department. But first of all, I would like to highlight that IDEME has been distinguished as Additive Manufacturing Excellence Center for Metal Materials by the CDTI. The CDTI is a national organism which aims for the industrial technology development. So this title strengthen our capabilities in additive manufacturing as reference center in Spain. So this is a project that we are carrying out all along with our partners, Kayak, Seid, and Lortec. Okay, so these are the 6 activities or the 6 additive manufacturing areas we are working on. I will go through each of them in the next minutes. So I will first go through technical consultancy. So somehow we act as a guide when certain company requires producing parts via additive manufacturing. So basically they come to us with a specific application, with a shape and some requirements. And what we do is we identify which combination of additive manufacturing technology plus material better suits with this study case. So once identified, we have to better understand how the part works so as to determine whether certain post-processes are required or not, or even if some changes in the geometry are required prior to the part manufacturing. If I will move towards design for additive manufacturing. So design for additive manufacturing is one of the key activities of the department. So as you may know, and as Olaf said, and as it happens for every conventional manufacturing process, AM has its own limitations and degrees of freedom. So for this reason, we will not make the most of a certain shape which has not been designed for additive manufacturing. So to our minds, this is the key to unlock the process and make them economically feasible for the industry. Our main goal here is basically, as I mentioned before, to transfer our knowledge to the company so that they can apply the design rules on their own. So we believe that training is compulsory to introduce additive manufacturing in the industry. Basically, companies should understand what are the limitations and the benefits of these technologies, and then they can wisely use these applications, these technologies. So let's see how is the procedure to generate an additive-friendly part. So let's imagine that we have a certain application. The first question that we have to make ourselves is whether the part must be made up of metal or polymer. So which material should be the part made of? So then we should decide which AM material is compatible, because not all the materials are available in additive manufacturing. And we will select this material based on the features required for the part. So in some occasions, we observe that metal is the material initially selected because polymers were not contemplated due to high cost of molds. However, IM brings new opportunities. So just for you to know, polymer additive manufacturing will save us approximately 10 times the money of a 3D printed metal part. So it is very important to assess what are the requirements of the part so as to use precise resources. So once the technology and material is decided, then we are ready to optimize the geometry. So as I said before, each technology has its limitations. Bearing in mind these limitations, we should reduce the volume and material of the part as much as possible. So somehow, the more parts we put in the build volume of our machine, the lower the unitary price of the parts will be. And that is due to fixed cost required in all the AM processes. So in the same way, geometry will help us to improve the part nesting in the 3D printing volume. So there are specific softwares that helps us to locate the parts in the build volume, as you can see in this image, just to make the most of the build volume of a certain machine. On the other hand, we can find techniques that will require superstructures, whereas some others will not. So this is something that we have to bear in mind. Geometry should help us to reduce those fine structures as much as possible, because basically they should be removed afterwards, as Olaf presented before. So this is kind of related to the fourth point, which is improving the post-processes. So basically, after the part is manufactured, we have to clean it. We have to even sometimes machine the part. We have to remove the superstructures. And these steps should be taken into account in the early first steps of the part design or the product design. So the last, AM is able to produce, as you have seen, very complex parts with organic surfaces, which might be difficult to control, to measure in the quality control steps. So we can interact with the geometry by including some features that can be easily measured afterwards. There are many options to optimize a geometry. Some of them have been already presented, but in these slides, you can see the most common. So the first way is the cut optimization. So basically, we can optimize a product from the very beginning, from the very first steps of the concept design. Provided that the design rules of the technology and the material that will be used to produce these parts are clear, then we can create an additive-friendly part by using a parametric CAD software like SolidWorks, CATIA, NX, or whatever. Then we have the topology optimization, which basically starts from a designing volume that we define, that will be this top 3D model. And then at this point, we should replicate all the mechanical and environmental constraints where the part will be working on. So, for instance, any temperature, pressure, forces, clamping areas, how the part will work in its environment. Based on this, the software, the topology optimization software will implement a finite element model and will relocate the mass on the part of the part in the areas where it is required. So this permits us to reduce the material and the part volume up to a point where we only use the material that the application needs. So the part has been optimized based on a purpose. And the last way of optimizing a part is the generative design. So we can see in the last few years that many softwares are including this option, this add-on, which is the generative design. And here, basically, the software itself generates a decision matrix based on the constraints that we put. So it's kind of similar than the topology optimization, but yeah, software doesn't present you only one option, but like a matrix of decision. So in this matrix, the user is able to increase or decrease the weight of certain variables, as, for instance, the part strength, the mass, a target mass, the stiffness, and some others. So in this case, the software is the designer, and we are the decision makers, let's say. So I just wanted to share with you some visual examples of applications that where design for additive manufacturing has been applied and that have been carried out here at IDEME. So this is a development that we carried out in cooperation with Scuti, and it's pretty interesting because this solution proposed to combine two different processes. So on one hand, a structural part made of titanium, you can see on the middle part of the screen, which is aimed to increase the product stiffness. It's the part in charge of the mechanical strength of the product. On the other hand, we have a polymer matrix that defines the product shape, that defines the case, let's say. And it holds the titanium 6.4 structural parts. So this product was initially designed in aluminum and completely manufactured in aluminum. And by means of additive manufacturing, we were able to reduce the part weight by 54%, sorry, and we were able to reduce the cost by 30%. This is another example where topology optimization was applied. So it is a topology optimized bracket. So we started from a matching part, which is this one, shown on the left, and ended up with an optimized shape shown on the right, this one, the gray one. So in this case, we wanted to assess the mechanical properties of a topology optimized part. We manufactured different versions of this bracket in different technologies like selective laser sintering, electron beam melting, metal parts. And the idea here with this was carried out within an internal project carried out at IDEME to double check that the mechanical properties obtained in this bracket were aligned with the results of the topology optimization carried out before. So in this case, we faced a very big part that was required to be printed in polyamide. It's an orthopedic corset for the medical sector. So this approach, the approach here was to reduce the part size in a first step by creating a structure like a frame here, that keeps the functionality. So in a second step, this frame was divided into smaller parts that were printed separately, and as you can see here, and glued together in post-processes. So as you can see in the screenshot, a very small height was needed to produce the corset, reducing in this way the costs. So if we would have tried to produce the part in a single geometry, it probably will have get the whole build platform. Okay. This is a very similar example carried out in the automotive sector, where they needed a checking jig for the trunk of the cars in the production line. So you can imagine how big this part is. However, it was manufactured in pieces, like you can see in the image, that were joined together, creating the final part. So again, this product was approximately like 2 square meters, and was manufactured in a build volume of 280 per 380 per 380. So otherwise, this part will have not been possible to be manufactured via additive manufacturing. So looking into the future, and yeah, here we are kind of aligned with Olaf. IDEME has planned to integrate new design softwares as Topology. Indeed, in the next few weeks, I hope that we will get the software, which brings new features to our portfolio as generative design, graded structures between others. So we can clearly see that the design for additive manufacturing is moving towards this kind of softwares that uses maths as a basis for creating these geometries. So moving toward material development, one of our pillars of the pillars of our department. So somehow, when you purchase a certain machine, it will be restricted to specific materials for what the hardware and the software of the machine has been optimized. So it can happen that new applications require new materials that are not available because there are not processing parameters, or because the hardware cannot actually deal with these materials. Okay. So in this sense, one of our research routes is the development of new materials for additive manufacturing. So actually, we do not formulate or we do not manufacture the feedstock, we don't atomize powders, but we adapt the AM processes so that the machines can produce parts with new materials. Okay. So in this slide, you can see at a site some of the materials that we have developed in the last few years. As you can see, not only metal-based materials, but also polymers and even compounds, concretes, and so on. So here you can see some of the materials that we have developed: pure copper, titanium alloys, nano-reinforced titanium alloys, even nickel-based alloys with a problem of hot cracking, polymers, resin-based polymers, powder-based polymers, and yeah, a project that we are working on currently to produce concrete, to manufacture concrete via additive manufacturing. So in this slide, it is schematically represented how a new material is introduced in an additive technology. So the first step is that we have to characterize the raw material in order to make sure that it meets the requirement of the system. So for instance, when introducing a metal powder in one of our systems, we have to check the particle size distribution, the flowability, the composition, to make sure that it is compatible with this machine. Okay. It can happen that the machine hardware is not prepared for this new material. So in this case, we modify the equipment, trying to adapt it to the necessities of this new material. So here you can see a clear example. This was a development that we did for the electron beam belting A2. And basically here we modified the hoppers, the way the powder is delivered to produce a titanium alloy, titanium aluminum alloy. So points 3, 4, and 5 are carried out simultaneously. Is the, let's say, the process parameter development. Okay, so it can take up to years to fine adjust the processing parameters of the machine, so that we can reach good quality parts. Okay, so in this phase we mainly observe. We start creating small samples, as you can see here, and we observe mainly the part density, the mechanical properties. It depends on the material, because, for instance, in copper we also check the conductivity. Okay, so it is an iterative process where parameters are progressively adjusted up to a point where material can be processed in a repetitive manner. And last, as mentioned before, in the design for additive manufacturing, we have to understand, we have to find the limitations of this process plus this material. So in this sense, we create certain artifacts that allow us to identify what are the geometrical restrictions of the process. And these restrictions in the end will affect in the product design step. So this is something that we can apply, that we should apply afterwards to avoid superstructures and yeah, to prevent some failures in the print job. Okay. So as a representative case of this research line, the material development, I just wanted to mention a development that we did in cooperation with GH Induction. So this company had the necessity of producing high conductivity parts, because basically they manufacture induction coils that they commercialize. So they need a material, a metal material with a high conductivity. So prior to this development, these products were manufactured by hand using traditional methods as cutting, bending, welding, for instance. So the main issue was that repeatability was badly affected because basically there were not two identical coils because of the human error. Okay. So we started the pure copper development for electron beam melting in 2014, producing small samples as I show below, these small cubes, and playing with plenty of processing parameters. So after 3 years of this development, the process achieved certain maturity, and it was then when GH Induction decided to invest in a new equipment fully dedicated to the production of induction coils, which is the Arcam A2X I talked before. So actually this machine was installed at IDIME, where it produces about 1,000 coils per year. So it's operated basically by IDIME, but the machine itself is from GH Induction. So the major benefit is that repetitivity and repeatability achieved by additive manufacturing is way better than by conventional manufacturing methods. In addition, the life cycle of the additively manufactured coils is larger as well. So in the end, they have reached a product which is more reliable. Okay. So if we look at the future of the material development, as Olaf said, additive manufacturing is presenting every year more and more materials because it opens new markets. So every year we observe that new materials bring new opportunities and new applications. So in this sense, we are open to develop new materials based on the needs proposed by certain company. So in parallel, we can see plenty of opportunities in different research and development calls, both at national and European level. So these developments will not only be focused on development of new materials, but also can be focused on the improving the performance of conventional material. And a clear example is the Titan project, which is a project that we are currently developing here at IDIME. And the aim of this project is to increase the productivity of titanium 6-4 process by laser powder bed fusion technology. Okay, so moving forward to qualification is kind of related to material somehow, because we have to qualify the process, to qualify the material in order to offer a certain quality to the parts that we produce. Okay, so Basically, qualification is a method to ensure that the combination of a certain additive manufacturing process plus a material is controlled, and the result of those controls are aligned with the standards and specifications set by the industry in a repetitive manner. Okay. So in this sense, we have to set the complete supply chain from the feedstock, from the powder, from the filament that the machine uses up to the final part. So after that, we must identify what are the critical variables of the process that will depend on the material, as I said, and then establish a procedure to fix them and to make sure that they don't change from build to build. Yeah, to ensure a quality control, right? So as a visual example, I will briefly explain how this procedure is in the case of the titanium 6-4 process in EBM or LPBF. So in this case, every single build, we should control the chemical composition of the material and make sure that the oxygen content of the processed material is below 0.2 parts per million. Otherwise, the part is weak. And this is tricky because sometimes if we are processing parts for the medical sector, you can imagine what happens if a certain implant made up of titanium 6-4 is below this value, or above this value, sorry, and the part cracks when it's implanted in the human being. So this is critical. So as a visual example, this is the general scheme that we always follow when producing industrial part from the material development, and the first steps of when the feedstock is analyzed and so on, up to the quality control and post processes applied to a part. So as you can see, this is a back and forth path that feeds back the previous steps in order to ensure good quality parts. And this must be done in all the technologies, okay? So technology development is also a strategic area of additive technology. So as I have mentioned before, we sometimes need to add new features to our processes. They can be aimed to process new materials, as I said, because a certain material requires some parts of the machine to be different, but they might be focused on other aspects. So, for instance, as increasing the productivity or improving the process of the post processes. So here you can see 3 examples. This is a project we did that produced wood-based materials. So we developed a complete setup of the machine. Here we included a induction coil in one of the metal processing machines to preheat the parts. And here, this is the Precision FA, which is another project where the aim was to modify the way the parts are welded to the build platform so that we can locate the parts in the post processes easily. Okay. And I bring you some examples of technology development that we have done here at IDIME. So a clear example of technology development is Custodian Project. This is an European project that started in 2018 within the photonics call. So this project is aimed to solve a very important issue that some nickel superalloys present during the processing the additive manufacturing. And basically, due to the fast cooling rates that these alloys present, they generate this cracking in the cooling rate phase. So these low weldable alloys present cracks, and the approach of Custodian was to tailor the conventional Gaussian beam, so the Gaussian spot, to a custom beam that helps us to mitigate this phenomenon. So this project is about to finish in September 2022, this year. Indeed, we are currently working with the custom machine where a high power laser, 4 kilowatts, was integrated in the machine, and a beam shaper that changes the Gaussian spot as well. So the idea is to deliver the power in a different way that a conventional LPBF machine does in order to get rid of these cracks. So 3D Sostenible is also a project related to machine development where we are trying to control the 3D printing of sustainable materials in the construction sector. So the aim of this project is to speed up the industrialization of these equipments of 3D printing in the construction field, in the construction industry, by controlling and automating different environmental conditions during the 3D printing processes. So in parallel, this project will also tackle a material development in certain way, because we are about to introduce reused waste in the concrete to minimize the CO2 footprint. So there will be a phase or a step where a new material will be introduced in this equipment to produce architectural shapes. So to conclude my speech, I will briefly explain our activities related to training. So as I previously mentioned, we believe that this knowledge must be transferred to the industry. Otherwise, IM technologies will not be integrated successfully in the value chain. So this is quite important for the industry. So for this reason, we currently offer 5 courses that are imparted in person. So this brings us the opportunity to transfer our knowledge or background in this industry with the added value that the courses, the people can get in touch with all the technologies that we have at home. So the courses that we currently are offering is additive manufacturing for non-technical profiles. So basic aspects of additive manufacturing. A specific course for 3D printing of metals, a specific course of multi-jet fusion and how to make the most of this technology, additive manufacturing for everyone, and one of the most important, which is the design for additive manufacturing. So as I said, we are trying to change the way we think the design and the parts. Okay. So as a new opportunity in this field, we have been distinguished as a center of excellence in metal knowledge. So CEX Metal is aimed to improve the competitiveness of Valencian companies, helping them to position themselves as benchmarks in the different markets in which they are present. So wrapping up my presentation, the main goal of our activities, as you have seen, is to bring these technologies closer to the industry and to help them to integrate additive manufacturing as a complementary method in their value chains. So thank you for your attention. I hope you enjoyed the presentation. So if you have any question, I will be happy to help you.
Thank you, Mario, for your very interesting presentation. And first of all, I would like to congratulate to IDEME to become a center of excellence in this area of metal additive manufacturing. If I will build a house, I will address to you to help me with your technology. I hope that it's movable because I'm not in Spain.
Yeah. I'm afraid it's early, but yeah, in the future we will be able for sure.
Thank you very much once again. It's really impressive portfolio of the technologies that you have installed in your facilities, and also congratulations to this. And especially this last slides about the education. I think that this is something that we also need a lot here in Croatia, because definitely additive manufacturing are the technologies of 21st century, and we have to educate properly our future experts to be able to use all the potentials of the additive manufacturing in this moment, but also to develop a new one. So this is really nice to see that you have really quite excessive list of presentations and education and training for the customers. If we don't have questions for Mario, Mario, once again, thank you for your presentation. And now I will invite Professor Clemens Holzer from Montana University from Leoben. I have to find you on the list of the participants to give you host rights. So Professor Holzer will show us experience of researchers from Montana University in Leoben in application of additive manufacturing in medical sector. So Professor Holzer, please continue.
Thanks, Damir. I hope you can see now my presentation in the presentation mode. Is okay?
Yeah, it's visible. Yeah.
Okay. Yeah, thanks, Damir, and especially to you and your colleagues for keeping this project together, for doing all this work, also now organizing this conference. Also regarding the words that you said about education, I think this is such an important project in this field, and it's not only in Croatia necessarily in Spain, but I think everywhere, of course, also in Austria. And we really have to educate in all stages our people, and I think there is such a big chance in using these technologies. As Professor Godet said, he would like to have a house produced in Spain. I guess he doesn't want to have one of the parts that I'm introducing now in my lecture. And I hope you never have the chance to get something like this. It's not so nice. I guess Olaf is already now in bed or going to sleep or playing his guitars. I hope that not too many students were listening to his presentation, because it's not so much about foolishing the iPhone, but it's much easier to fool the professors for the students than in the lectures, in the online lectures. So they will only sit some head in front of us and maybe sometimes moving eyes. And we believe the students are carefully listening to what we are saying. So this is also some kind of future. And as some of you said, it's a little bit frightening, especially the last pictures that Olaf has shown. And also one thing was very important for me, that he showed this table that post-processing, pre-processing, post-processing is about half of the effort and half of the costs. And I think especially in a project like this, what I'm showing you, I think the pre and post-processing is 90% of the effort and 90% of the cost. So actually the additive manufacturing and the machine itself is only a very small part, and I think I will show you this. And also what Mario said about material development, I also have to emphasize that there are not so many groups working on polymeric implants, directly additive manufactured. And one of the biggest reasons, I think, is that there is so few material available. And in medical applications, we don't have the chance to develop our material, because, you know, the registration process for materials in medical applications is so long and so costly. So we only can take the materials that are on the market. And this was very disappointing for us at the beginning when we were thinking about these applications. There is also not a high interest of the companies developing new material. But on second thought, I think it's quite clear, because, I mean, we would use maybe 20 kilos a year or maybe 100 kilos a year. But for this 100 kilo, no company is willing to spend a lot of money for developing a new material. And also regarding the risk, because if there are any problems, of course, the material is very important. So there would be a lot of money involved. And so we are, as you might see, then we're very restricted on our material. Okay, I would like to introduce a project, a specific project that we're working on since a few years. It's called CARMED, and it is together with some partners, especially with the Medical University in Graz. Short presentation of the project, and then I would like to go into the process and tell you a little bit about the particular projects that we're doing within this big project frame. So this is the project, and we try to establish the whole chain of additive manufacturing in the clinical setting. And this, of course, is a huge chain. So we have to start with the data from the patient itself. We have to treat this data so we can use them. Then it's also about how you get this data, how you get images from the implants that you would try to produce. Then, of course, it's about FEM, and then it is about selecting the right material for the specific case. We have to optimize the additive manufacturing process, of course, and also coating is or might be an option. Of course, we have to understand what is the mechanical, what are the mechanical properties, and then we have to go in vitro and in vivo biocompatibility tests. And those tests then are finally deciding if we can really go into clinical trials. And this is the final goal of all this process, to do our additive manufacturing in patients in the hospital. So we have two areas in this project. The first area is additive manufacturing with polymers, and there we have three projects in this area. And the first one is dealing with rib replacement. The second one is with orthodontic implants, and the third one is with craniofacial implants. And then we have area 2, and area 2 is dealing with the inorganic materials, so with metals and ceramics. Again, we have the rib replacement, but then we have individualized plates for trauma treatment and also scaffolds and trauma surgery project. The rib project is the biggest project. It's a strategic project for us. So there's no decision how we will do this rib replacement, with what material, what would be the best material. Of course, there are a lot of questions to be solved. And so this is this strategic project done in both areas. And of course, there are some other parts of this project that we have to do. I will only stay focused on the polymers, of course. If you take a look at the partners, yes, there are a lot of partners contributing. It's a huge project, and of course, it's also needed. So we have a 3D printing partner here from Styria, which is doing material extrusion, 3D printing. We have company Arburg, for example. We have Evonik for materials, and so on. I would like to follow the workflow that we have. So when we start, I mean, designing is then a little bit different. On the one hand, what we have heard now from Olaf and Mario, but of course also the design is especially important if you design an implant. So we are always starting with the patient data and how we get the right design for the part out of it. Then there's the additive manufacturing, and then there is the clinical implementation. And then along this workflow a little bit more in detail, I will tell you about the segmentation of the patient data, how we get this data, how we treat this data. Then in the additive manufacturing part, it is about material selection, also based on the results that we get from finite element simulation. Then we have to optimize our production technologies. And always we have to pass the mechanical and cytotox testing before going in the clinic. Then there will be preclinical testing. And finally, there should be clinical pilot studies. So it's data from data to part. I will show you this in the workflow now. I will go a little bit more in the details of those two in the project of the bone. So when we're talking about implants, and craniofacial implant is the project that we are following the longest time so far, it is all about that you have a lesion, that you have a hole in your skull, maybe because of an operation of a tumor, or maybe because you had an accident. So there is some bone that must be replaced. And of course, you have to start with imaging this this part of the body. So this is usually done with CT. One of the challenges here is to clearly separate the hard stuff, the bone, from the soft tissue, so that we can get the data that we then need as a 3D model. So we have to extract this bone from the soft tissue. We have to clear the bone itself, so that we finally have at least a model where you see here, for example, a lesion that has to be filled with the implant then. There was also a lot of thoughts how to construct this lesion, because of course everybody is specific, and you cannot just make a geometric solution. So one approach that we followed, and it was very successful, is that analyzing a lot of skulls and then using intelligent software to at least semi-automatically suggest how this implant should look like afterwards. So as you can see here, the lesion, and then we have the implant, so this should fit perfectly to the head itself. Okay, so finally we have the finite element, we have the design of the part that we have to do. Of course, the first steps of the AM processes is just as we were before. We have to select, and we have to optimize and to apply the right production method, and we have to select, adapt, optimize the polymers that we have. Then we have to prove the sterilizability of the selected polymers, which is of course a go no-go criteria, and you also have to check if the sterilization has an impact both on mechanical and on cytotoxic properties. Mechanical characterization has to be done with the parts so far produced, and also the biocompatibility has to be tested. So at the end, we have also the possibility to select coatings to get a better integration in the body itself. So the materials that we have, also according to our technologies, are especially we have these two ranges of materials. We have the high temperature material, most of all PEEK, because PEEK is well introduced in the medical applications. And it's also the reason why the surgeons work with this material. It is not because it's the best material, it is not because it is the most similar material to the bones, but it has been introduced a few years ago and it's working quite well. But of course, with the high temperature polymers using, you have the challenge to have a optimized printer for this. And as you know, there are not so many printers on the market that are really working at high temperatures perfectly. On the other hand, we have our standard temperature polymers that we can produce quite easily, but we have to prove that, for example, PMMA or also polypropylene and so on are materials that are adequate to the mechanical properties, for example, that are expected from, for example, an implant in the skull. For the 3D printing technologies, two technologies were used here. The first one is the material extrusion technology. So we have cooperation with the company Appium, which is providing the high temperature filament extrusion machine, and we have Hage, which has also developed a special machine for medical material extrusion, but in the lower temperature regions. And then we are working with the Additive Freeformer. I guess you might know these machines. The biggest advantage here is that we can work with the granules, so we do not have to take the filaments, because having filaments with medical application grades is even more difficult than to use some granules that are already used for injection molding. Yeah, you can see here the Appium printer printing here the implant with a lot of support material. Also, this I think was a very important input from Olaf. I think we can learn here a lot. Of course, we have the Additive Manufacturing Center already installed at the Medical University at the Clinicum in Graz. So this is very close to the operation halls, and this is also the goal I didn't mention before. Of course, you always have the possibility to get all this data from a patient, to send this data to a company who would produce the implant, usually by machining, and they will send then this implant to you, to the clinicum. And this all takes a few days or maybe a few weeks. This is not so important. Important is that the patient has to have two operations. So the first operation is usually cleaning all the skull, in this case, and then getting the data, then everything is closed. Then after a few days, the implant is here. Then the patient has to be operated again. Meanwhile, everything's moving a little bit in the head. So the surgeons always have to adopt the part that they got. So our goal is to produce the implant immediately during one operation. So this should be fast enough, and this is the reason why we have this additive manufacturing center at the clinic. Then we have this Harburg plastic freeformer with the big advantage that we can use the granules, just the standard granules, and of course also a huge, a bit wider variety of the materials, also together with the software that is provided by Harburg for designing the parts and the production. I already said sterilization, washing, autoclaving is a big issue because, of course, not all polymers are stable enough for these temperatures or for the methods that are used for sterilization. So this is also an issue to test this. Surface roughness has to be adopted, or has to be good enough for the implant itself. And then we have to do the testing. And as you can see here, this is also done here at the Modern University, at the Institute of Polymeric Testing. There was designed a special holding setup for the implant itself, so the implant can be tested non-destructive, so only for cyclic load application and stiffness and deformity is recorded then, but we can also do this much faster and doing an impact test and of course destroying our implants. Of course, there are also done standard testing. Standard tests means with the standard specimens, so not with the implant itself. So Charpy, bending, tensile testing, of course. Very important for quality control is to understand what or how looks the implant inside, and this is controlled with micro-CT. So in this case, you see ripped parts and some red spots that you might not see that well. Here you see the implant for the skull and with all the porosity that is still inside the part. Biocompatibility tests have to be done because, of course, the implant, the material, but also due to the production method, there shouldn't be any negative immune response or inflammation, of course, to the implant itself. So also tests with living bone cultures were done. And of course, since we are in the clinic, the whole process has to be monitored quality-wise. So the quality management has to be established, the process chain for doing this, and also proving what has been done and how it has been done and has it done correctly, which is of course quite a lot of effort that has to be put in there. Just showing you a few topics on this. We have to design the process map, and then there has to be a lot of, for example, done to, for example, document management. So there is some software needed for this. You have to do a standard, you have to define a standard process for the process documentation. This is together done with the Technical University of Graz and the University Clinic in Graz. For every process, there has to be an exact description and there have to be standardized operating protocols. It's of course, it's not so different from maybe producing an industrial part, but everything is a little bit more in detail. Everything is a little bit more challenging doing here. Doing a lot of work putting in here. So finally, clinical trials have to be done and are the goals for the near future. So understanding the workflow, I would like to show you now some project, and I would like to start with the rib replacement. Of course, I wasn't aware that this is a big issue, replacing ribs in patients, because there are no solutions so far that really working well. So it's just a little bit, you might see it here. If you have broken a rib, if you have some problems in your thorax, then usually those replacements are with metals. Metals are much too strong. So after 1 year, after 2 years, there might be deformation of your thorax due to these forces that you imply with these replacements and so on. So there is a big need in understanding how do you replace the ribs and what are the properties that are needed there. So again, we have the workflow. Patient data imaging is done, already finished, and also the additive manufacturing technologies, we are more or less finished. So we are about to go in the next step for the clinical trials. So that's what we are talking about, and it took us actually a long time to get the simulation of the thorax, because it already looks like an optimized part now, and of course we learn a lot from biology, but to understand what are the properties that are needed for each rib. And you see the thorax is consisting of a lot of ribs and very different ribs, and some are interconnected, some are open, some are quite small, and other much bigger. The first idea was just monitoring the movement, understanding the dynamic movement of the dynamic of the thorax. It was just to image this with patients. But actually turned out that this was the most challenging part of the project, because it is moving a lot, and there is a lot of stress, of course, coming from this. And we had the idea to just go to the clinics and make CT images, but the problem with CT images is of course ethics. So if you cannot justify that the patients are X-rayed for second or third time, you cannot do it just for research. So there was no possibility to get this data. So the possibility is also to do it with MRI, but then we had the problem with the surrounding tissue. It's not so clearly to separate the soft and the hard material. And then there are some special kind of patients where routinely they get 2 CT scans, but in the first year that we had now, unfortunately, fortunately, there were no such patients. There was also the idea just to make, some marks on the skin and register how the body is moving, how the thorax is moving, what happens if you lay on the side, what happens when you're coughing. The problem is that we need the movement of the thorax bones itself. And of course, like everywhere, we have not only bone, but we have all around soft-ish tissue. So if you just put some marks here on the skin itself, you do not measure the actual movement of the bones, but you measure the whole system, and this was not exact enough. So based on this problem, there was a great idea coming out of the clinic to work with body donors. And that's the part that I really do not like on all this project. And so for those of you who are sensible, you can skip the next slide. So you can close the eye if you don't want to see something like this. So we were really working with thoraxes taking out of corpses. And yeah, we had the chance to do this in cooperation with the various departments. You can open your eyes again if you close this. And those thoraxes were taken out of the body, they were intubated, they were ventilated, and of course with this thoraxes, CT images could have taken in every position and without any problem. But more or less the whole thorax then was really used up. So the bony thorax was then extracted. The first step, the whole thorax, including all the soft tissues, the muscles, was investigated. Then also the muscles were resected, and taking a look at this. Then the thorax was stretched and the markers were fixed then on the sternum, the bone itself. And then there was all the different movements that have been done. All 12 rib pairs have been extracted. And finally, all the mechanical tests with these ribs have been done to determine the properties that are in this specific thoraxes have been found. Of course, you see here, this is also very similar to normal mechanical testing, but with very specific specimens. So based on this data, finally we get the finite element model of the whole thorax, including all the relevant geometries, strands, and also E-modules, thanks to the partner CAE. And also the additional data that are needed to understand the whole system, because you also have the muscles, you have the pleura, you have the surrounding skin, which gives extra properties to the thorax itself. And then the different movement sequences could have been simulated. For example, active breathing is not that crucial, of course. We were all thinking that if you get, for example, when you're playing ball, you get a ball on the thorax, this might be a big impact, but actually the mechanical ventilation only has some burden for the bottom ribs, and we could measure this quite well. The biggest forces that we get on our thorax is laying on the side and, for example, cuffing. Then you really get pressure in there. That's how you see that now we have a thorax model. We can work with this. We can try to understand what ribs need to be replaced and what properties would be needed for replacing these ribs. The model was created, the whole thorax, but also with the soft tissues around it. So we have also allocated stiffnesses. Cuffing was then, of course, challenging because especially after the operation, after the surgery, it is very important to not have high pressures. But what we are talking about, what is high pressure, cuffing was not possible to be done with these body donors. So there were some other methods tried just to find out what is the pressure that is applied on the thorax when we cuff. Also, this has been done successfully again with the specific department of the clinic. So now with the ribs, we are quite finished with the data collection. We are done this with simulation solutions with CAE. We have the complete thorax model, and we can simulate now ribs produced with different materials. So this is really perfect now. So there was a lot of effort. I think it was more than 2 years, then only finally getting the conditions for how to produce or how to design the part that we need. Okay, now once we understand this, of course, we can do our printing trials with FFF and ABF. That's, for example, like realistic print ribs look like after having been printed here. Okay, so this was for the rib project. I already mentioned the craniofacial implant is the project that we follow the longest time. So that's what we're talking about. We're talking about the implant on the skull. We are just about to go into clinical implementations. All the necessary steps have been done. All the necessary permissions have also been granted by Ethics Commission, for example. So in the first place now, the first material that will go into patients will be PEEK, and they will be followed by the low temperature polymers. So the challenges here were the fast and exact collection of the images. So everything has to be done within one operation, and then the lesion reconstruction should be done best possible. Every now and then one is talking about mirroring, so from one side to the other side, but as you also might know, we are not symmetrically built, so this doesn't help that much. So the problems also here is that we have the body fluids, that we have the soft tissue, that it's not so easy to really get an exact picture of the skull. So what we did was scanning a lot of skulls, more than 100, and I'm trying to understand with deep learning approaches done together with the Graz University of Technology, what is a normal skull? So what would be a good approach if we have a standard skull? And standard skull then also has to be defined. Is it from children? Is it from men? Is it from women? And so on. But this working was not yet satisfying, but it's ongoing work and it's not so bad. Then we also have done the experiments with body donors. Again, we recorded everything to get the data, especially also regarding the wet tissue. So what can we remove? What can we put aside? How can we get the segmented and cleaned data that we then need for the CAD model? And again, the additive manufacturing of the part finally is the easiest thing to do, or is the best understood thing that we can do. So with this approach, we only have a very little post-processing for the custom fit implant, which is crucial for the patient and especially for the surgeon standing in the operation hall. So how can we select materials? For example, here with PMMA on the one hand and PEEK on the other hand. So we have the 3 different machines that we're using. Mario already mentioned that we always have to do the qualification process for each process, of course, which takes some time. So we have the polymer testing with all the different geometries, and usually done in high numbers so that we can really be sure what we will get out of this. Of course, it's easier with standard specimens than with the real implants that we then have from some patients. Sterilization processes have been done, mechanical analysis after sterilization processes, cytotox procedures has been done, and micro-CT, as I have already shown you, and in some cases also coating and so on. So what is the outcome of the washing and sterilization procedure? Since we are doing this with formaldehyde, there is the question, has been the question of the formaldehyde release, how much uptake will be done by the material, and will then this be released in the body in the worst case. So the good message is that after clinical washing and sterilization procedures, we had no influence on the mechanical characteristics, for example, on 3D printed PMMA, doing all this tests like here. Also with the microscopy and the microporosity has not been changed that much that there should be any problems. The influences of the freeformer were even a little bit better than with the FFF. So again, this is what we're desiring for what we are going to. Of course, and there we are at the angle how we print and how we do this. It is depending the testing with peak here on the various positions how we produced our parts. So horizontal, vertical XY, or vertical in Z direction, how they break, and so on. The good message also from our tests were that we had no significant differences in mechanical characteristics of the commercial manufactured cranial peak implants, so machined, compared to the 3D printed one. And also, of course, for the peak implants, we have no effect of the steam sterilized ones. And we also can see this here in the microcities. The commercial, it's also interesting that usually you get the implants with these holes in the implants, which actually comes from I would say from the beginning of producing these implants, and they are still being done. So there's no necessity to do these holes in the implant itself. So they are also not included in our FFF printed parts. And you can see that if the non-destructive tested, the commercialized, untreated, and sterilized, there are not any significant differences. So this is the proof that we can use these implants directly in the patients. Cytotoxicity after sterilization is still an issue. So we have to take a look how good or how fast the cells are destroyed by the sterilization, but also how good or how well is the cell viability after we have the sterilization. So is there any toxic effect or not? So both manufacturing technologies lead to a release of formaldehyde directly after sterilization. So this is more or less cytotoxic effects on the cells, even after 24 hours of sterilization. ABF has slightly better results, but it's still challenging to do the right sterilization process, also that is available at the clinic itself. So what are the next steps for the craniofacial implants? We have to implant them in an environment for neurosurgery, also having a lot of thoughts how to screw, how to fix the implants in the skull as well, because also the screws that they use there are very specific screws, usually especially developed for the material. Of course, we have other options here as well, but we have to check them. We have to optimize the formaldehyde, and we would like to increase the density of the printed samples so we can prevent the inclusion of the formaldehyde. So the preparation trials already started within 22, and now we are about to have the next patients, or we have to have the patients in these trials. Finally, we have the orthotronic implants. We're talking about the cleft implant. This in the mouth here. This is the project where we have the least progress. This was the project that we started the last time, the latest. Here again, the patient data imaging is very challenging. We have to define a standard operating protocol to get this data. Again, you cannot do too many scans. You cannot access this a few times because this would be dangerous for the patient itself. So that's where we're standing here with the imaging. So the challenge is that when we're working with low X-ray doses, the images itself are very imprecise, and the exact designing of the palatine cleft is not possible. So CT images would be best option to get the necessary data, but the X-ray loads are too high. So also here we will follow the approach with deep learning from skulls that we can get from the Department of Anatomy, female and male skulls, and then do these scans and learn from these standard scans then how the design of the palatine cleft might be possible. And the goal is then using the DVD with the low X-ray doses, getting enough data that we can learn from the poor data that we get from the scanning with the deep learning and with the results that we have from our standard skulls, that we can design the palatine cleft. Okay, so I hope I could show you that this is a quite challenging project, that additive manufacturing needs a lot of pre-processing, post-processing if you're doing this with implants. And of course, we have to think about what are the success factors bringing a project like this into the clinic. And of course, the successful factors is very easily said is the cooperation between the different disciplines. And you can see here a lot of different people really coming from a lot of very different backgrounds. And only with this, many people here, we can work together successfully. As you might also have the experience going to the clinics, we have to learn the language of each other. So engineers and physicians not always mean the same if they say the same words or if they talk about some topics. Of course, we have to cooperate. And also in this special field, it is the science and the one thing. So what can we do? But then we have to transfer this not in the industrial application, but into medical application. And this is also quite challenging. Also quite interesting to mention is that the different publication cultures that the physicians and engineers, for example, have, and the matrix structure of the working groups is also a very important issue. We have to deal with this. We have to learn to deal with this. But of course, this is also getting a lot of input, for example, from the ceramic colleagues, from the metal colleagues, how to look at different problems, how to look at different solutions. Okay, so I just would like to sum up. Of course, it's additive manufacturing of polymers, but what it makes it really challenging is to do this for implants. We have these different projects with different speeds in the project and also with different progress. A lot of processes have to be viewed at and taken into considerations. And there is always open questions with risk management, with the approval process, and with the clinical implementation. With this, I would like to acknowledge my colleagues, most of all Lukas Henschel from my chair, Sandra Petersmann, who did all the testing here at the Universität Leoben, and of course the Medical University in Graz with Professor Ute Schäfer, and the whole project was financed in Austrian funding system. Thank you very much for your attention.
Presentation. As you already mentioned at the beginning, that you hope that, and I also hope that no one of us will need this type of application of additive manufacturing. But on the other side, it is good to know that you can count on patient-tailored implants, for example, for certain parts of the body at this already at this moment. So I will also show one smaller project for cranioplastic implant in our pilot project in next part, but with already known material, bone cement. The only special skills that you have to apply there is designing for a patient. So thank you very much, and I'm not sure if we have a question for Professor Polzer. As I can see, there is no question. Thank you once again for a nice presentation. Now it's almost 12:30, and according to our agenda, we will have a break until 12:45. And after that, in second part of this conference, Israt Rumana Kabir from Brunel University in London will show you application of geometric dimensioning and tolerancing for additive manufacturing. And in last presentation, I will show you a few industrial projects as a result of this INEX-ADAM project, as a result of new gathered knowledge in 3 specific fields: tool making, medical sector, and transportation. Thank you all presenters for interesting presentations, inspiring presentations, and thank you all participants for attention. And please come back in 15 minutes and we will proceed with the conference. Thank you. Hi, everyone. I hope that you all have the opportunity to refresh yourself and that you are ready for our 2 last presentations from today's conference. And the first one will be from Israt Kabir from Brunel University in London. And the topic is geometrical dimension and tolerancing for additive manufacturing. Israt, are you there? Yeah. Okay.
Yes, I am here.
I will make you a host.
Okay. Just let me put my. Yeah, I think I can share my screen now. Okay. So can you
yeah, we can
see my screen?
Yeah, we can see it.
Okay. So let me put it in the presentation mode. Okay, just put it like that. Yeah. How can I like put this off? Okay, anyway, is it okay with this bar? Yeah. Okay, all right.
Okay, it's okay.
So shall I start? Okay. Yeah. Thank you so much and welcome. Good afternoon. Welcome back to this final conference from INEX-ADAM project. My name is Israt Kabir and I am representing UBRUN here. My supervisor, Dr. Eugene Pei, unfortunately, he sent you apology, not being able to attend this because of his college something meeting. Yeah, he needs to present there. So today I'm going to talk about the review of geometric dimensioning and tolerancing for additive manufacturing. Last year, at the beginning of last year, so we started a project on geometric dimensioning and tolerancing for powder bed fusion from collaborating with Damir, Professor Godec from University of Zagreb and Dr. Nordin from Lund University. And UBRUN took part in review process of this GDNT technique. So I'm going to give some highlights in what's happening in this area and what's the future opportunities possible for this. So yeah, before starting the main topic, just let me give you a snap of the Brunel University London, where actually we work from. So it's located in West London of United Kingdom, which is very close to the London Heathrow Airport, and the place is called the Uxbridge. It's a good, well-connected nationally and internationally. And we have a pretty big campus, including the students' accommodation as well, and all buildings for different departments and institutions. So if you see that roundabout, so this is the main entrance of Brunel University of London. It's called Kingston Lane, and on your right, this is the main reception, and these are the student accommodation, these building blocks. This is the athletic center. It's used for the different sports events, and also for the students, that creates the like Great Britain Olympian sometimes. And yeah, if you go across this road, there are a few establishments also belongs to Brunel University, and I sit somewhere here. It's called Michael Sterling Building, where the Brunel Design School sits. This is a brief background about myself. So I am the research associate of INEX-ADAM project, working with Professor Godec and everyone else for last 3.5 years in additive sector. And after my doctoral program actually done in City University of London, where I developed finite element model for laser surface hardening process in optimizing processes and also predicting surface properties. And also you can use to select the appropriate materials. which later I transferred the methods I have applied in my PhD. I transferred it in developing teaching material on modeling of function graded additive manufacturing technique. I have my first degrees from materials and metallurgical engineering. So I have expertise in materials characterization techniques for qualifying materials and also selecting for different processes. So today's talk consists of the general overview of geometric dimensioning and tolerancing for additive manufacturing, where we are going to focus in powder bed fusion. And also we're gonna talk about, the lattice structures, which one of the most adopted geometrical features and leveraged by the capabilities of additive manufacturing technologies, and is using in different important engineering applications in aerospace, medicals, automobiles, and others, and which actually has a huge property property to reduce the weight of the material and also reduce the waste of the material used in additive process. But there are need of developing various GD&T technique to ensure the quality production of such structures by additive manufacturing, and we try to look up briefly from our work. So starting with the basic definition of GD&T, not only for additive manufacturing, but also for other engineering manufacturing process. So this is actually GD&T is a kind of language. It's a communication technique for the design or for the product description, right? So it's communicate the criteria and constraints of a product, comes from the customers, and communicate through the different development stage of the product. And at the end, it's finalize the quality of the part to ensure the geometrical conformance, to ensure the accuracy, fit to form, and the geometric properties, including the allowable variation of the process. In my right hand side, you can see this is the general representation of GD&T of any mechanical part. So this is a mature area in terms of engineering and design or manufacturing process. Started very beginning of the 20th century by a person called Stanley Parker, who realized the need of finding out need of creating the GD&T concept so that you can avoid the misleading information from the customer to the manufacturer. And there are huge significance of this GD&T. As I already told, it's ensure the fit to form, the geometrical accuracy, the geometrical property, the accuracy of the geometrical properties, also the quality of the parts and allowable variation can be caused at different stage of the manufacturing processes. And also it's important in cost and cost effectiveness and time efficiency, because it's allow you to avoid the disqualification, reduce the number of disqualification of parts or material wastage and resources. So how the GD&T is implemented in manufacturing. So there are, over the years, by research and hands-on experiences from the users or industry people, there are standardization developed so on this GD&T methods and techniques for different kind of manufacturing technique, for example, casting, forging, machining. They have also some specific type of GD&T requirement, and it's all added to the general GD&T requirement for the manufacturing industrial part, as well as for additive manufacturing. And you can see that, sorry, let me just minimize this. You can see that here that after this 2010, there are standardized texts coming on, especially for the digital manufacturing or additive manufacturing technique, which talks about this characteristics, geometrical characteristics for additive manufacturing, design, digital product definition, and also some test artifacts, which is the coupon or geometrical model to quantify the tolerancing and dimensioning for additive manufacturing. Especially this ASME 14.46, the product definition for additive manufacturing, which is created or extended from the ASME 14.5 and dedicated to additive manufacturing. So it's addressed the process-driven requirement for GD&T, for example, the build direction or gravity direction, the layer thickness, and also it's addressed some intricate features for patterns, infills, assemblies, but it's still in the development phase. So there are lots to do on this like in future. So why actually additive manufacturing require the new GD&T standards? It's because of it doesn't comply with the existing GD&T techniques, which usually followed from ISO 1101, or I showed you that why ASME 14.5. It's because of it has a unique capability to produce complex free-form shapes and also different kind of design freedom. And also the additive manufacturing processes come up with different varieties in terms of technological aspects, in terms of processing materials, and most importantly, like the personalized or customizable design, right? So there are issues in tolerancing methods or technique came from the additive manufacturing process itself, also generated due to its diverged capabilities. For example, the build direction, support structures, the effect of support structure on surface finish, and the effect of various materials using in support structure, effects of post-processing for removing support structure on geometric quality or surface finish. And also additive manufacturing has capability to process multiple materials. So the interaction between two materials, for example, differential part shrinkage or dilution, or for the fusion based technique, the residual stresses for multiple materials. So how it actually contributes to the tolerancing the variation of the final part in geometry and how you can actually control them. So all those things need to be addressed if you improve the promotion of additive manufacturing. And there are different capabilities, for example, adding topological optimized features of curvature, various curvature or complex planes or shapes, internal channels like in conformal cooling, and pattern or lattice structures of various shapes, right? So all those have a different type of design specification require different kind of tolerancing issue. This here I showed you some of the common GD&T evaluation criteria or characteristics corresponding to representing some, the tolerance, and also corresponding to the geometrical features. And you can see that the general 5 types of tolerance can be related to those kind of profiles or geometrical elements here. But some of the geometrical elements I put very least number, but there are a lot coming from the AM, like overhangs, the minimum like very thin channels or lattice structures, very and there is a micro additive manufacturing process there. This is also making things difficult in terms of GD&T, and we need to come up with the type of tolerancing technique or the process for this AM. So there are 2 ways of existing in the additive qualification of additive manufacturing in terms of GD&T. One is the predictive approach. So it's done at the design phase using the CAD models and using simulation or different kind of mathematical model to find out the allowable variation or part shrinkage or the residual stress or other things. And there are other approach, which is the experimental method. You can qualify the process and the part for additive manufacturing by using a model, a 3D model containing different geometrical features for quantification of the tolerances or uncertainties and variation. So these and using different measuring technique like CMM or scanning or optical measurement technique. So in that experimental technique, you use test artifacts. As I told you, it's a model contained different various geometrical features, which corresponding to the different geometrical characteristics and tolerances. Over the years, so in early 90s, 1991, so people started researching on finding out appropriate benchmark artifact for additive manufacturing for different kind of process. I picked few GIBTA, which I call GIBTA, the geometric benchmark test artifact for, especially for the powder bed fusion. So you can see that here, Kruth So one of the earliest or pioneering research group who studied JEPTA for powder bed fusion techniques. These are this JEPTA is used in developing standardization technique for tolerancing for powder bed fusion. And there are different kind of geometrical feature. You can see that the round hollow cylinder, the steps, the different scale of the component. You can see that diamond shape and this kind of things, which gives you a little bit example that the capabilities of additive manufacturing, although this is not very complicated. But here in recent development study for AM or powder bed fusion, you can see few of them which are actually using the lattice structures and pin and hole model for characterize assemblability. And here you can see that there are some GDNT test artifacts which is dedicated for application. So these test characteristics or test artifacts also varies for different processes, for different application and different materials, and researchers and most importantly different design features. But researchers are trying to find out that towards to making more standard test artifacts which actually can be satisfy the GDNT experimental process for maximum AM processes, or for covering maximum design features. So this is also a challenge in this area is going on there, and there are opportunities work on it. And actually our project also we are trying to move to this way as well. So I already have been telling you the challenges related to GDNT for AM. That some of the process, because of the process itself, the nature of the process, because it's a additive process, it creates the parts layer by layer, and it has differential part shrinkages and isotropic properties, and also like the different process chain has the tendency to contribute to adding the variation. For example, like the converting the CAD models to the machine readable model. That means this when you slice the model, right? So there are different slicing parameters influence the nominal CAD design when it's making the model ready to print. And also there are some technological issues, factors that can contribute to the variation. For example, the automation technique and different kind of control mechanism, of the tool path. Here I am going to show you few of the literature studies for addressing few issues and finding out solution to overcome them in terms of different additive manufacturing for GDNT. So people, I saw that people maybe worked on those additive processes which is mainly fusion based, and we know that material extrusion doesn't give a good surface finish. So people also looked on this process, and also this is comparatively inexpensive additive manufacturing technique to research on, and can be used in different type of application. So for example, addressing the challenges of the deviation of CAD models and the sliced model, the STL model. So how people are working there, finding the way of converting the slice model to the CAD model, including the variation, after the slicing process, and also finding out the effects of the slicing parameters, and so that they can predict the allowable variation in the final part, printed part, and can minimize or control them during the design process. So people are working on this, and people also making like developing different mathematical models, such as skin shape model, which contains the CAD design model, so containing the design description or product description, including the allowable variation. And you can simulate this model. You can exactly quantify very different, quantify the variation in different scale, because it's a point cloud based technique. So it gives you the discrete geometrical data. So people are working on that and trying to find out, mitigate the issues at the design phase, development phase of the products, so that they can control the like the variation as much as possible before the production. And you can see that one work corresponding to the VAT photopolymerization, and it's now manipulating the voxels dimensions, so tiny voxels dimensions, to find out the the effects of the slicing parameters on the tolerance for the final product. I will go to some studies about the powder bed fusion, but why actually we are focusing on powder bed fusion in this work, because powder bed fusion attracted various engineering application, including aerospace, medicals, automobiles, tooling, which actually some of them are our interest, the projects inclined to, and it can treat various type of materials, especially the metals and alloys, can be used making various mechanical parts. There are different variation of powder bed fusion techniques based on heat source fusion mechanism or processing materials, which gives you more complex factors could be influencing the tolerancing and dimensioning of the process part. That could restrict, and that's actually restricting the, it's a restriction in the wider uptake of the process in the industries, because the powder bed fusion process itself is very expensive technology, and if we cannot ensure the part quality, so it's not very worthy. So some of the works regarding GD&T of powder bed fusion, here they're trying to find out the uncertainties related to different stages incorporating in the tolerances or geometric variation. For example, in simulation phase, in modeling phase, due to the different modeling technique and software capability, and also the simulation phase, due to the inaccuracy or inadequacy in parametric optimization, And also from the measurement phases, so there are few technique we can actually measure or quantify the tolerances experimentally, which has their own limitations. People also working on, so as I told you before, there are basically two approaches people are working on. One, predictive analysis using modeling and simulation to quantify the tolerance, and also the experimental technique using the test artifacts and measurement machines. So they are trying to find out the deviation between these two approaches and optimize the processes. There are some feature-based design framework are suggested in developing more appropriate test artifacts for various technologies, and also incorporating the integrate or complex shapes and the features like assemblability or lattice structures kind of in the test artifacts. So now moving to lattice structure. So we are going to link this GD&T requirement to the lattice structures, because this is a very impressive area or design component can be leveraged by AM in different applications. So lattices is it's a German word. It's a kind of crossed woven structure, can be made by metal, wood, or even the clothes, like the fabric, right? People do that. And it has been used actually very early time in engineering application. That's why I showed you this. This is a bridge, railway bridge. I think it's one of the structure of 19th century in the UK, and still there because of its strength and strength, so higher strength to weight ratio. You can see it's in a very large scale lattice structure. But here in AM, we use the lattice structures at different scale. We can, as it is very scalable with the additive manufacturing production, you can use in different shapes, forms, and in different application for water purification, filtration, heat exchanger, light weighting in the different aeronautical space components, and other, right? So, but the GD&T issues coming from these lattice structures are more complex, and we are trying to find out that where the large gaps are and how could it be, like what opportunity it's create. Here I tried to classify lattice structures which can be found in different CAD modeling software, so which is used in designing AM part. You can classify various ways the lattice structures, and you can find in various shapes, forms, and or patterns in nature. But I classified, like I got it from the literature, like what conceptualized that there are mainly two kinds of lattices, which is periodic, gives you a very continuous or repetitive pattern, and which is the stochastic, called unstructured, mainly it's called foam or honeycomb. In this diagram, you can see that this lattice structures I classified in periodic, pseudo-periodic, and random based on the unit cells or the pattern used in different CAD design software. Okay, and what kind of different unit cells are there used in producing such kind of lattices. So So going to the next slide, here I showed you the design software, which gives you the opportunity to design this such lattice structure, including the further analysis for simulation or for topological optimization. So we used in our project the N topology and NetFab in our work, but here are actually several softwares has different capabilities of design and simulating lattice structures for producing for AM. The application, I tried to show you few which is already been tried in the industry. For example, this is an unhuman unhuman drone, the fuselage of the drone, and it's created the honeycomb infill by 3D printing technique, and you can see the tire for automobile, which is the heavy duty kind of, and gives you light weighting so that the car can moves in very bumpy road. This is the insoles. You already midsoles. Actually, it's not insoles, it's midsoles. So Adidas already implemented this technique using the carbon printing machine, and there are bone implants and many others, aerospace engine parts and other parts are actually turbine parts can be made by using the metal additive manufacturing and lattice structure. These are few application, and the main characteristics is the lightweighting and scaffolding. So you can use in cooling purpose and filtering purpose. I already told to you. I found that among the 7 standard processes, there's 5 processes basically used in the production of industrial parts or consumables. For example, you can see this. This is a turbine blade, but it's an end part used in powder bed fusion, which is the new beam technique. And you can see this is the implants as well you can produce. This is a multicolor structure, lattice structure produced in binder jetting process. And this is the inside the rubber frame, like the rubber support of helmet, a motorcycle helmet. You can see that this is also produced in VP technique, so which gives you light weight but lots of shock absorption capacity. And this Rideau, they are using this in producing their consumer part. So next, I'm going to show you the GD&T studies and issues related to the lattice structures via additive manufacturing technique. And I already mentioned that the conventional GD&T is inadequate for additive manufacturing process, and also there are lacks in correct tolerancing process for lattice structures or integrate shapes, including non-uniform thickness lattices, especially if it is functionally graded, and then conformal lattices, and also the unstructured lattices. The tolerancing issues, you can the people are addressing due to the lattice structure is size tolerance due to the strut thickness for different unit cells, dimensions, and form or position tolerance for different shapes and patterns, or and repetition. How would you like, if it is structured or unstructured, and the orientation tolerances as well, like the strut between individual strut, and also the between unit cells. Some recent studies addressed the issues for tolerancing method of lattice structure, and actually all of them followed one technique which is actually added to the standards in 14.46, which is the total supplemental surface concept. So the total supplemental concept surface gives you an imaginary surface between the inside the allowable tolerance zone, where actually the nodes of the lattice going to land in or connect. And so you can allow the deviation of the nodes connecting or landing within that zone by so it's a kind of datum, okay, so which you can control the printing of the lattices, especially conforming with the surfaces or boundaries. There are people finding out the capabilities of different measuring techniques, because lattices could be very small scales, so micro scales. So how the what measuring technique could be efficient. And also they are trying to find out developing standard test artifacts, including this pattern features or lattice features. So these are the area people are working related to the GD&T of lattices. So I almost came to the end of my talk, where I'm going to summarize that what actually I have been telling for now. So I told it, so in a nutshell, that GD&T for additive manufacturing, especially that creates the integrate shapes or complex features like lattice structures, is very important. And it is the answer to increase promotion of the process and gain the trust from the user. There are a lot of areas to work on, especially people did not try, like people did not try, people tried very small scale and finding out the industrial based test artifact, which is related to application based. I can relate to, but yeah, there are work need to be done here so that you can pay more attention to them, and the industry's requirement in terms of additive manufacturing uptake, and also the the comprehensive GD&T information related to its traceabilities, standards, and a standardized test artifact. Like there are huge area we can work on as well. So that's all. We also trying to along with Damir and Excel, we are trying to come up with a solution with our test artifact using aluminium alloy, but this is a still ongoing process, and hopefully we will continue with it after this project as well. So thank you so much for listening, for your patience. Any question now or after, please feel free to ask. Thank you. Thank you, Damir.
Thank you, Isat, very much for your interesting presentation. And this is clearly shows that we can expect even more research and projects in this field, because the documentation of additive manufactured parts is not sometimes that simple like in traditionally produced parts, which you clearly showed in your presentation. I cannot see any question here. So Israt, thank you, and thank you, Dr. Pei, for your effort in this area, and I hope also that we will continue our cooperation in that field in the future. So now
Thank you.
Thank you, Isat. I'll reclaim the host, and in my last presentation, I will try to show you briefly a few industrial projects. I hope that you can see my screen. A few industrial and medical projects that we finished within INEX-ADAM project. Thanks to the new gathered knowledge and expertise from our partners. As you already saw, all of them are really experienced and highly skilled in their field of expertise. So I should say that we really learn from the best, at least in Europe, if not from the world. So in next few slides and next few minutes, I'll try briefly show you a few projects realized here in Croatia. And as I already mentioned at the beginning, at first presentation, our goal is to apply this new knowledge, advanced knowledge of application of additive manufacturing in 3 specific fields. It's a transportation, it's tool making sector, and medical sector. And I will beginning with 2 projects from transportation sector. The first project was realized with our large company that are producing trains. So we deal with the railway sector, and our task in this project was to optimize a bracket for this emergency egress device. As you can see here, this is a state of art now. So it's a current situation that in this company they are producing this bracket from welded plates, and our task was this bracket consists of 5 elements. Our task was to try to consolidate this product, so to reduce the number of parts, as well as to try to minimize the mass, the cost of production, and so on. There were a few requirements, and also we were free to think about changing the material, because these one are steel plates together welded, and we were free to select a new material. But we have to be aware of some of the regulations in railway sector oriented to passenger safety. So the material, for example, if we will use polymer material, this material has to be flame retardant. So just in short, this is optimized part, as you can see here. We managed to consolidate 5 pieces product into single piece product, showed here in this slide on the right side, with weight reduction compared to the initial one for a 64%. But this is the data because this huge reduction of the mass is also because of the changing the material, because of changing from steel plates to the Ultim material. And this is a Stratasys material that is a new one. And then recently they get some certificates that this material is approved for application in the railway sector. So this is not flame retardant material. And after this project, industrial partner decided to purchase their new, the first one, 3D printer. So this was the, I should say, milestone for this company for getting into the world of additive manufacturing, which is also, I should say, a good result from this pilot project. Not only optimization of this part, but through this project, they realized that additive manufacturing can, that they can benefit a lot from application of additive manufacturing. I don't have information if they already have installed the first 3D printer in their company, but if not yet, it will be very, very soon. Another project from transportation sector is from area of drone or unnamed aerial vehicle sector. And here on this slide, you can see already optimized in the first step design of the drone, because those booms of the drone were produced from polymer composite material. And this was already reduction of the mass compared to the initial one made from metal. But okay, we were not satisfied with this result, and we tried to optimize all the elements of this drone in second step, again in a with similar goals. First of all, try to reduce the number of parts of this drone, and the second, try to reduce the mass, which is quite important for this type of the product. And here you can see one example of topology optimization of the drone boom made by software from Altair Inspire. And here you can see also lattice structure on the main body of the drone. So this is on the left side lower part, and on the right side is the upper part. And for generation of this lattice structure, we also used another very powerful software already mentioned today a few times. It's Topology. And here you can see the printing of the lower part of the main body of the drone, so that you have at least a feeling about the dimensions. I didn't mention it inside of this presentation, but as you can see here, even with the low budget 3D printer, desktop printer with FFF technology from PET-G material, we managed to produce the complete parts of the drone. So as you can see here, 4 booms, lower and upper main body part of the drone. Just a summary of results of this project, of this optimization. We managed to reduce weight of the part of the drone more than 40%. This relies only on the data about the material for the housing, for those parts that we optimized. Of course, those motors and some electrical components remain the same. So it's not the total weight saving, but in case of those parts that we optimized. So also we managed to consolidate this product from 16 parts at the beginning to only 6 parts at the end of this stage of the product. And here you can see mounted drone without upper half and completely assembled here. But we were not satisfied with this stage. So in next phase, it's not shown here, and the project is not finished yet, but we will try to create a drone from only one piece. Again, we will try to reduce the mass with topology optimization and try to test the both versions. Now, in case of tool making, I'm not sure how, but probably in some other countries, not only in Croatia, tool makers are traditionally oriented, traditional businessmen, and sometimes it's very difficult to convince them in something new. So we try to cover the most projects from this area. So you will see a short presentation of 4 different pilot projects from this area. So this is something very similar that you saw already from Israt presentation, but also Olaf mentioned something about the gyroid lattice structures. In this project, we cooperate with our industrial partner. It's Metalska Jezgra from Čakovec. They had EOS powder bed fusion technology. So we used aluminium as a material to produce different type of potential mold inserts in order to find the optimal density of the lattice structure within the insert. So we use the gyroid from few reasons, gyroid lattice structure from few reasons. The first one is already shown by Olaf, because here you see you can have a quite great potential for heat exchange. And sometimes in molds, for example, for injection molding, this heat exchange is very important and influence a lot on final properties of the part as well as production cycle. On the other hand, the gyroid structure is isotropic structure, so you can expect the same properties of the mold insert in all directions. And the third reason is, as also Olaf mentioned, that this is a self-supporting structure, so we don't need to apply support structure and after that have a problem with removing it. So we try with different densities of the gyroid structure, and then compare by 3D scan all of them and compare it with the CAD data in order to get the information which density of the this lattice structure will result with the best possible results, the best possible matching with the CAD models. So here is okay, for I didn't mention for generation of this lattice, we also used Topology software, and for inspection we used GOM inspection and 3D scanning, also from our industrial partner from Čakovec, from Metalska Jezgra, and this is the optimal result from our research, that with unit cell of 5 mm and shell thickness of 2 mm, we can obtain the best possible results. So this is not maybe strictly tool making project, because this can be applied generally, for example, in mechanical engineering, but this is the closest to the tool making sector, and there are some of the ideas that we have from tool making sector, which was putting a task to our research project in this case. In second tool making project, we try to optimize properties of the injection molded part presented on this image, because it's a thin wall part, and many of thin wall injection molded plastic parts tend to deform after ejection from the mold, which can be observed as a warpage of the part. So in this project, our task was to optimize the cooling of the mold in order to get the best possible results in case of deformation and warpage of the part. And of course, you can also expect that if you will use, for instance, conformal cooling, in this case, that you can expect a shorter cycle time. But the cycle time was not primarily the task of our optimization. So we have to generate in software for a simulation of injection molding process 3 types of simulation models. The first one included cold runner system, so-called cold runner system. It's a system through which thermoplastic melt is fed to the mold cavity. We also generate conventionally or traditionally cooling channels that were planned for a traditional tool-making approach. In second step, we generate a simulation model with conformal cooling channels, and again with the cold runner system. And in third case, we change a type of cold runner system. We change position of the gate, and we use a so-called hot runner system, which means that the material within the runner system will not be a waste material after the cycle is finished, but this material will be pushed into the cavity in the next injection molding cycle time, because the elements of the mold in this hot runner system is heated, and the material within this system is maintained on the melt state during the whole processing time. So this is only a summary of our results. It's a cross section which shows us clearly temperature gradient or temperature field within the mold. And you can see some of the differences in temperatures. For example, here you can see this is a movable part of the mold. It's a core, and it's heated on a higher temperature than, for example, the upper part of the mold, which is a cavity. This is a core, lower side, and the upper part is a cavity. In this case, we have a better situation, and I should say that maybe the most uniform distribution of the temperature can obtain in case of a hot runner system with conformal cooling channels. And here you can see a warpage of the part. Okay, I must warn you that those deformations are not real. They are 10 times enlarged for a presentation, for a more clear presentation on this slide. So finished product will not really deform that way. The deformation is 10 times smaller, but for a clear presentation of the critical part, we can set on our program for a simulation the scale of deformation that we want to present. And you can see here, okay, we also have some deformation in case of conformal cooling with the hot runner system model. We also have certain deformation, but the maximum deformation is the lowest one compared to the variation with traditional cooling and with conformal cooling and the cold runner system, and which is more important, those deformations are more uniform, so you can more easily adjust. First instance is to adjust some of the processing parameters, but the second one, which is very often these days in tool making sector, is that you will produce a mold with the core and the cavity, which are not, for example, flat, which are deformed, but on opposite side as a negative of the deformed part after the simulation. So this is a kind of a deformed parts produced in the mold. The next project from tool making sector was also for injection molding, but in this case, production of application of additive manufacturing in production of short run or small scale production mold produced or with polyjet technology from ABS-like material. I must say that we have in maybe last 1 or 2 years few inquiries from the industry for production of small scale production, for small scale production of the products. And on first instance, someone can suggest, okay, we can print it. Why should we produce a mold for production of, for example, 50 parts? Today we have faster machines, so from economic point of view, 3D printing, for example, with Hewlett-Packard MJF technology is probably more reasonable than producing the mold. But you have potentially two problems in this type of the projects. First of all is, can I make a part with this additive technology, for example, from PBT with 30% of glass fibers? Probably not. So, although almost every day we can witness the development of new materials available for additive manufacturing, not all materials that are available, for example, for traditional processing, not all of them are available for additive manufacturing. This is one problem. So you cannot produce a part, for example, from PBT with 30% of glass fiber with additive manufacturing. So if you need those parts, those 50 or 100 parts for certification of the future large-scale production product, then you must have the product with the same material as the material that will be used in large-scale production. So this is the first problem. But even if you can find a material within the additive manufacturing technologies, for example, polyamide can be found with the powder bed fusion technologies. The principles, the physics of the processes of injection molding and 3D printing or additive manufacturing are quite different. And you also can, again, expect, even if you will use the same geometry, the same material, or almost the same material, but the principle of building those parts are different, you can expect, in some cases, differences between final part properties. Therefore, again, if you will use this part for certification, it's not maybe advisable to use additive manufacturing for production of those 50 or 100 or 200 parts. So there is a reason why we carried out this pilot project with one of company from automotive sector to produce a mold for short run production, small scale production. And here you can see two different parts within the mold, two different cavities. Okay, their principle is prior to certification of a future product, they produced on traditional way small prototype mold with 1 or 2 cavities, but even this mold is simplified compared to the mold for large scale production. They have to spend a few weeks, maybe months, in order to get the prototype steel mold. In our case, we were able to produce this mold within 2 days, and then within 1 day to adjust some of the inserts in this mold. So the result was maybe 7 to 10 times, we can be 7 to 10 times faster comparing to the traditional approach to the production of the prototype tool. Okay, it was our learning curve in this project. So in first attempt to produce this type of mold, we produced 3D printed mold without any changing of the existing CAD of the mold. So we just copy and paste into the additive manufacturing. We produce it plastic mold with so-called tunnel gates here toward both cavities, and after the first shot on one small injection molding machine, one of them broke, and soon after another one. So we learned that we cannot apply design principles that are standard for traditional steel molds in case of plastic molds. So we have to redesign the mold and print it again. But if we are looking on the accuracy of the 3D printed technology that we used here in this case, you can see here red numbers are from CAD data, and those black numbers are real measured part. And you can see here that the dimensions are quite acceptable for a tool making sector. But we have another problem. After this is a injection molding machine together with mold. But after the injection molding of the few parts, this is the part produced from the first mold. You can see here the remaining of the tunnel gate here, and thermoplastic part here covered the broken piece of the mold. But we also can observe here a lot of flash, and dimensions of the final part were not so accurate as the mold. So which means that this material of the mold is more compressible compared to the metallic steel molds produced in conventional ways. So this is maybe not a good choice of the material, not good choice of the geometry for this application, which means that if you will use, for example, additive manufacturing in tool making sector and use plastic material, you will have certain limitation in this area. And next project also will show you that. In this case, our task was to produce a mold for sheet metal forming. In first step, we used FFF technology and PETG material, but after the very first cycle, after the removing the metallic part from the mold, our mold was broken, and therefore we decided to rebuild the tool for this sheet metal forming from better material for Ultem. And after that, in second cycle, we managed to produce at least 20 parts with this mold before it was became useless. And finally, we have also two pilot projects with the medical sector. The first one is producing production of a cranioplastic implant. I will not spend too many words on this one slide, because Professor Holzer already told you a lot about data acquisition and segmentation and so on. But we have a real patient here in this project. Unfortunately, technologies that we that are available, that were available and are available today for us, cannot use certificate materials that can be built directly into the patient. Therefore, our approach was indirect. In first step, we produced mold for casting of the implant inside the mold, so a negative of the implant, and then in second step, during the surgery, the implant was cast into the mold and installed into the patient. So this is a presentation of the segmentation of the patient data, and here is the area of the implant. This is the CAD design of the mold on the left side of the slide, and on the right side, 3D printed mold made from PolyJet 3D printing. And during the surgery, inside the surgery room, the implant is produced immediately before the installation into the patient. My question was for the first time why this implant is not produced maybe 1 or 2 days before, sterilized and so on. But the answer was that this bone cement has already integrated antibiotics within the material, so it is very important that the patient receive the whole dosage of this antibiotic, and this antibiotic is released immediately after the combining of the 2-component PMMA material. This is basically PMMA material, so this implant should be produced few moments before integrated into the patient. And here you can see adjustment with some titanium plates and bolts into the patient. I did not warn you for the picture. My apology here. And the last one was from our colleagues from hospital center here in Zagreb. They had a gamma knife where they have a lot of dose distribution measurements, and for this setup they're using phantoms together with inserts in which special types of detectors should be installed, and those detectors has different shapes, different requirements, and they are very expensive, and also those inserts are very expensive, and sometimes you have to wait for a really long time to get it. So in this project we tried to test a few technologies that were available for us for production of inserts for those detectors, and our colleagues from the hospital tested, and they were very satisfied with the obtained results, because the fit of the insert and the detector greatly influence on the results from dosimetry measurements. So we also accomplished here very good results. So this is only a short review of 8 pilot projects that we managed to finish during our INEX-ADAM project, but I hope that in the future we will have more of such projects, and I hope that we will manage to open maybe a new fields. I know that we have one project with that deals with additive manufacturing of food, which in the morning showed you Olaf. So okay, we are not from the construction field, but maybe we can also participate in this type of the project. So thank you very much for your attention, and if you have a question, I will be happy to answer you. Thank you. So if there are not the questions, maybe we have in our agenda a time for a discussion about the additive manufacturing, the future of additive manufacturing, some thoughts about maybe future cooperation, future development in this area. So every one of you is invited to make your contribution in this discussion. Maybe I will say a few words at the beginning that I think that we need. First of all, as I already mentioned in the morning and after Mario's presentation, that we will really need more education in this area for our future experts. And as Professor Holzer mentioned, which is very important on almost every level, from maybe primary school and more intensive with the higher educational level. So I can announce that here at our Faculty of Mechanical Engineering, we are now in development process of a new study program. And we will have at our chair, at our department, a study for polymer processing and additive manufacturing. And I hope that students will recognize our program. But even through some of the programs in earlier stage, it is necessary to inform, at least to inform and to get a basic, to give the basics to the students, basic information about the additive manufacturing, because as you witness, those are technologies of 21st century. Those technologies are one of the pillars of Industry 4.0, and I think that we will not be able to imagine a future without those technologies. From this project, we point out only maybe a small portion of potential and benefits of using of these technologies, and I hope that in the future there will be more and more. As Professor Holzer mentioned, the development of new material, and also Mario and Olaf, the development of new material will probably lead to maybe a new revolution in manufacturing and in application of products that were not that were not feasible in the past, like for example those gyroid lattice structures. So we really need to pay attention to education of the young people, because today if we have a student and he will get his diploma paper with 25 years, age of 25, he must be employable for next 35 to 40 years. It depends on the system from country to country. If we are speaking about the children in primary school, then they have to be employable even more after the finishing this school. So I think that we have to prepare them for the very fast changing, I should not say a market, but okay, a market of different type of jobs, and some of them will, I should say, die with the time. But for example, additive manufacturing will offers a new type of jobs in the future. So I think really that this is important, and not, I should say, not to organize, to establish a system, educational system only on a field of, for example, on this, I should say, micro level, like our study for additive manufacturing, but also in national and maybe international levels. So maybe I'm not sure how is with the experience with some other countries, and is there any ideas, suggestions? You are really all open to discuss. You can unmute yourself, because this is this type of a meeting, so that everyone can take active part in this discussion. Once again, I just would like to thank all of the presenters and all the participants to the patient. So, but now you're free to discuss about anything you think that it's important for the future of additive manufacturing, for future cooperation, education in this area. You're welcome, please.
Actually, I'm not understanding your question correctly, because you're asking about the cooperation between countries. And I think INEX-ADAM is such a great example how all contributed to gain knowledge, how important it is that we see the different views of different groups focusing on different details, approaches, and sharing those experience. And I think really this has been done perfectly in INEX-ADAM. And although I was thinking about how important education is, I didn't go that far like you, because you mentioned the pupils in the elementary school already, and you're right, we also have to train them. But I think we are on a good way, and also this cooperation that we have here is just perfect. So let's continue in this style, or let's continue exactly with this. So this is also a thank you, a big thank you to everybody in the project.
Thank you, Professor Holzer, for your words. Well, we have a few, I should say, programs, but those are not systematically built into the system, educational system of in our schools. But we have some programs for the pupils already in primary schools, and they have a lot of ideas. And when they realize that they can perform their ideas into the, and to hold them in their hands, it's something that will attract them more to those technologies. But of course, this type of the program should be very carefully designed. So we have really few initiatives here, also in secondary schools. I know for our faculty, maybe some other faculties also aimed to be more dedicated to this technology. And I think that, for example, our faculty for construction should also think about it. We have 4 technical faculties here in Croatia, so probably they must start to think about, if not yet now, about changing some subjects in their curriculum, so that they can introduce at least some general information, basic information to their students. Because in next maybe few years, a student which will finish mechanical engineering study without any knowledge about additive manufacturing, I think that it will be an incomplete person for their professional tasks in the future. Is there maybe someone else wants to say something?
Damir, thanks for the organization, all the presenters. Many thanks about the very good and nice presentations. For the education, I see in our technical schools, they are already doing it. Now we have some program in some secondary schools, where, for example, in the course of geometrical design, they are also going just to look at the possibilities of additive manufacturing to see how it can be done. And so therefore I think that over time it will be more incorporated into the education, also into the schools. I don't know, mentioning primary schools, that's a little bit of a toy play around there. Perhaps you can do it with these 3D print toys. I think you brought it once to Leoben.
Yeah.
So that it's a more playful starting with it, but on the serious side, I really think that they will go on with it also in the schools. The biggest challenge is changing the minds of the adults who are doing the constructions, because they think of conventional production, and they don't go into the freedom of the design, what is possible with additive manufacturing.
Yeah. And thank you, Stefan.
Changing there is a little bit harder, I would say, than to go with the child's from starting on with all the technology.
Yeah, thank you very much for your words. I completely agree with you, and not once I said in not so far history that first of all we have to change our minds, and we have to start to think outside of the box. Olaf is really great in this type of thinking, because during our stay in Land 1 week with him, he shows us really good slides which opens some different perspectives of the same thing, but we have a completely different, I should say, look on it. So this is something that we have to change in our minds, and then try to educate new, at least we who are working on the faculties and universities, and change the way of thinking, try to change the way of thinking of next generation of the experts. And I hope that we will have every day more and more projects available for this type of approach of education. Unfortunately, I invite a few ministries to our conference, and we have at the beginning one round table. I also invite a few ministries, but it's obvious that it's not interesting to Ministry of, for example, Science, to Ministry of Economy, and so on. So sometimes this less interesting of this type of institutions can be an obstacle for systematic changing in some of the areas. I should say here in our area in educational way. But I hope that in the future we can do as we can do in our limitations, and then try to introduce this additive manufacturing in the most level that we can in the education, from the earlier age up to the long life learning.
Of course, you're right, and it's a pity that the ministries are not here, but I have to tell you that you are nevertheless very lucky, because you have at least a connection to the ministries, and you think at least about inviting them. It wouldn't even come into our minds, because we know that they are not interested here in Austria.
Okay, it's relief to me, because it's not only a situation in Croatia. Thank you very much. Is there anyone else who wants to say something? Well.
Hello, a little bit. I'm coming from Polytechnic Krapina, not anymore in Health Polytechnic. I'm not anymore there, because we started our connections when I was the professor on Health Polytechnics. Now I'm only in Polytechnics in Krapina, and only I want to tell you that we need more information, not me, because I find you somehow, but I think that I'm here because I'm interested in that, because we have the study of transport logistic and transport logistic as well. And when I have seminars with our students, with my students, in fact, about, we call that, let us say, three-dimension printing, because it is more popular in the beginning, because they don't know. Then I found that they are so interested in that, and that they found, and some of them, some secondary schools, they have also the they have first information, but with cheap printers, and they don't know how to use. But me, myself, time to time, I'm trying to compare these technologies with biomedical engineering, let us say, because I'm more deeply in that. You can find everywhere you can use this technology everywhere, not only in transport, medicine, and as you say, molds. So I think you have to work more and more about information, to come on these all conferences, to make not conference as you have. We met on the completely different conference. I know that colleague Katalenic Miodrag knows very well where we met. And it is very interesting because you came and show us. And it is interesting to come on the different places, not so close only that, to find, to give the possibilities to people to find you, to know about you, to give them information about these technologies. Thank you. That's all from me.
Thank you very much for your suggestions. Thank you. Do we have maybe someone else? Well, if not, I will say once again, thank you everyone from today's conference. First of all, presenters, and then all participants. And this is not our last meeting. I'm addressing now to the project team. This is not our last meeting. I hope that we will have the opportunity to cooperate on many more projects. And I'm announcing you a short meeting as soon as we will get the information from Springer Nature that the book is published, so that we can discuss about also this project. And it's quite great effort from all of us. It's almost 300 pages of the book, and really a huge effort, not only for writing, but also for collecting copyright permission, which was really a nightmare for some of the figures. Some of them were changed, but okay, this is a normal process. And thank you once again to all of you, to the great support during this project. We really learn a lot from all of you, but I hope that you also learn something maybe from us or from other partners from this project. And I hope that at least from our ADAM platform, we will have opportunity to cooperate in the future again on many more projects. I would like from additive manufacturing field, but also from some other fields. This is not the only technology that we can deal with. So once again, thank you all of you for great support, for many useful information, knowledge that we gathered together, and stay safe, I should say. Okay. Dražen, okay, are you here?
Thank you very much.
Thank you.
Thank you all. Thank you, Daniel. Goodbye.
Bye. Bye.
Goodbye.
Bye.
Thank you.